apologise, we had about 90 minutes to film everything on location before the next thunderstorm rolls through, so enjoy the show. I'm about to step onto brand new land, and admittedly, yes, it is a little bit underwater right now because, well, that river there is in flood, but 50 years ago, this would have been open water, and I would have been jumping off this boat up to my neck. And yes, I was extremely nervous about that little jump because that's the first time I came off here. But yeah, this is the Wax Lake Delta. 50 years ago, no trees, no plants, nowhere to put your feet. I would have been swimming on a coastline that's famous not for building up, but for eroding. And to explain why, we have to go just a little bit inland. The Mississippi River is so murky and brown because it's filled with silt and sediment. Throughout history, roughly every 1,000 years or so, deposits of that sediment build up enough that the river basically blocks itself and then takes a different and steeper route to the ocean. At least until silt builds up on that new route and the river moves again. That massive and relatively sudden change is called an avulsion. And avulsions were fine until modern times, when the industry that you can hear and the livelihoods of untold numbers of people rely on the river being exactly where it is. But in the past, every time that humans have tried to fix the rivers around here, there have been unintended consequences. We built levees like this one to protect towns like Baton Rouge here, but they make the river flow faster and higher because all the water is now concentrated into one channel. And because they restrict water flow, they move the flooding upstream, which means that the next neighbourhood over has to build their levee higher to deal with it. There are regulations to prevent levee wars when communities have to keep building their levees higher because their neighbours are doing the same. Those regulations aren't always followed. And downstream, levees mean that instead of a wider river during floods, you get a faster river, eroding away those silt and sediment deposits, literally washing away the land that it once created. And now the river doesn't flood as much, so the ground next to it dries out and settles and sinks. Louisiana's coastline is disappearing. In 2011, government cartographers retired 35 place names, taking them off the maps, because those islands and bays just don't exist anymore, they're just open water. But there is one place on the coastline, a couple of hours south of Baton Rouge, where land is appearing again. And that is also an unintended consequence. Which brings us back to where I was standing at the Wax Lake Delta.
The Wax Lake Outlet is a channel off the Atchafalaya River. The Atchafalaya River is a channel off the Mississippi. So a channel off the Mississippi River. Excuse me. I heard a little thunder.
Okay, no,
let's get out of here. The Wax Lake Outlet was built in the early 1940s, and it was designed to pull water off the Atchafalaya River and reduce flood stress on Morgan City. One of the unintended consequences was the development of a delta at the mouth of the Wax Lake Outlet. And so the Wax Lake Outlet and the Atchafalaya River carries a lot of sediment, and then when it gets to the coast, the river flow slows down and all of the sediment in the river settles out. We're talking tens of millions of metric tons of sediment every year. This is solid enough land that you can walk on it and you can stand on it. Louisiana has lost nearly 2,000 square miles worth of land over the last century, and there's a large effort to rebuild the coast. A big part of that effort is to try to partially divert the flow of the Mississippi River to create new deltas that are like the Wax Lake Delta. And so people like myself want to study the Wax Lake Delta so we understand how deltas build, so we can better design coastal restoration projects. It's important to restore the coast, one, to push back the sea, to enhance flood protection in Louisiana. And it's also a place where you could potentially bury carbon. You know, we have too much CO2 in the atmosphere, and highly productive deltas like the Wax Lake may be one of those places where we can do that. I often feel like the numerical models that we have to understand the coast are pretty darn good. The much more difficult thing to model is to understand people and how people are going to behave with this changing coast. And I feel like that we barely even know the equations. We don't necessarily know even what the rules are to govern how do people deal with a stressful, changing environment.
So yes, it's still wet underfoot here right now because this whole area is still in flood. But that just means there's more mud, more sediment being deposited. This land is going to be a couple of centimetres higher, and this coastline is going to be just a little bit safer. I've sunk about an inch into the mud and it's gone in my shoes. It's in my shoes. Right, I should totally go with the sandals. Oh, all right.
Oh, wow. The Parkes Radio Telescope here in Australia is most famous for receiving pictures from the Apollo 11 moonwalk, but it's still in near constant use for As petrol and diesel get phased out and batteries become better and cheaper, electric trucks are slowly starting to become a thing. But the trouble is, you need a massive battery in each truck, plus the infrastructure to charge them all. It'd be great if you could somehow charge up electric trucks while they're on the move. Well, the world already has a proven, tested solution for sending power to massive, fast-moving vehicles. Electric trains have pulled power from overhead wires for more than a century. So why not put those wires over the first lane of a highway and let trucks connect to it while they're on the move?
So it's been running for 21 months now and will be at least for the next year. A full-scale scenario for Germany would be to equip 1/3 of the German highway network, and that could reduce 2/3 of the greenhouse gas emissions by heavy trucks. But for sure there are pros and cons in the real world, and we want to be sure before we are going into the future with such a system. There were a lot of safety concerns in the beginning, so we had to discuss everything with fire brigade and police and so on. We have the voltage level of a tram, and the electromagnetic fields are lower than on a tram, so that isn't an issue. Overtaking is absolutely no problem. You just set the indicator or leave the lane, and the pantograph will automatically drop down immediately, and then you're free to go. So in that part, a battery or the combustion engine will take over, and you will have the full power without interruption.
One of the things that's really obvious sitting here is that the technology works. Like, we're running off grid power now, and it's really, really quiet in here. There are two main uses for big trucks like this. One is last mile delivery, picking up lots of items from warehouses and taking them out to individual shops. Most of that is going to be away from the trunk road network, so e-highway wouldn't work for that. But those trucks tend to take shorter journeys anyway, and they're sitting idle at night, so those could charge at the depot. The other use for big trucks is taking containers from ports to warehouses, or from one depot to another. Almost all of that traffic goes along big trunk roads like this, and that could all be converted to run straight from the grid, with batteries taking a couple of miles to each end. Roll that out, and suddenly you're replacing a lot of diesel.
What you're doing is bringing the electrons to the vehicle in a cable rather than trying to carry them in a box in a battery. It's the most efficient solution, the most efficient use of energy. We think that it's possible for the system to pay for itself. It's possible to set an electricity price sufficiently cheap for the truck operator that the lower costs will pay for the additional costs of the lorry in about a year and a half, something like that. And we think that it's possible to use some of the money that comes back from electricity sales to pay the infrastructure provider in a way which will make that an investment that's fundable by private finance. And we think there is enough money left on top of that to pay a tax to the government to replace fuel tax. Where you've got real difficulties is some of these journeys into really remote parts of the country. And there's a strong case for saying, look, in some of those journeys, let's have a hybrid vehicle. But the majority of the system works very well on very efficient electricity, and you can do it quickly. So I think that's an attractive thing to do if you can.
We've had more than a century to develop delivery infrastructure that's based around combusting fossil fuels, and that's going to end in the next couple of decades. Britain is planning to ban the sale of new petrol and diesel trucks by 2040, which sounds like the far future, but it's actually only 18 years away. The rest of Europe won't be far behind, and building those wires above enough roads could take up most of that time, if that's the solution that's chosen. So right now, we know the basic technology does work. That's what's been tested here. But a lot of things that technically work can't be built economically. If we want to keep to that date, then the UK has somewhere around 3 to 5 years to figure out if this is just a gimmick, or whether it's worth investing the billions that it'll take to roll this out. Personally, I try not to give predictions about the future, but I wouldn't be too surprised if those wires become part of everyday life on the road in the next couple of decades. If you want to know where you are, you can check on your phone. It listens for signals from whole constellations of satellites in orbit, and by triangulating all those signals and using a lot of maths, it works out where you are and shows you a little dot on a map. But how do the satellites know where they are? There aren't any landmarks in orbit for them to refer to. If satellites are in a high enough orbit, well away from the atmosphere, then they can predict their position. They'll just keep orbiting in about the same path. There's no atmosphere to slow them down. But that's not precise enough. There will be distortions caused by gravity from the sun and moon, or even from mountain ranges down on Earth. So maybe they could use the other satellite signals, like GPS. But if they're all relying on each other, that could steadily drift apart from reality. Maybe they could track the stars or the features down on the Earth, but that's not precise enough either. At some point, something down here on Earth has to look up in the sky and work out the position precisely. And one of those somethings is hidden away in the countryside of southern England. It looks like a regular observatory, but it's not looking at the stars.
We track man-made satellites in various orbits doing various jobs. They all have to have special reflectors on that enables the light to be returned to us. And so we can measure the time of flight, and from the time of flight derive the distance. You send out a very short pulse of laser light. You do that 1,000 times a second. Each of those shots, because you're using such a tiny short pulse of laser, it's 10 picoseconds long, which is about 3 millimeters. That's the limitation on your precision. So each shot is about 3 to 4 millimeters precision.
This station works round the clock whenever the sky's clear. That's why I'm here today. There will be some genuine observations when the clouds break, but right now I'm not actually disrupting anything. But it does look significantly better after dark.
Because it's a laser, it's a very specific wavelength, so you can filter, and that's what lets you work in day and night.
As petrol and diesel get phased out and batteries become better and cheaper, electric trucks are slowly starting to become a thing. But the trouble is, you need a massive battery in each truck, plus the infrastructure to charge them all. It'd be great if you could somehow charge up electric trucks while they're on the move. Well, the world already has a proven, tested solution for sending power to massive, fast-moving vehicles. Electric trains have pulled power from overhead wires for more than a century. So why not put those wires over the first lane of a highway and let trucks connect to it while they're on the move?
So it's been running for 21 months now and will be at least for the next year. A full-scale scenario for Germany would be to equip 1/3 of the German highway network, and that could reduce 2/3 of the greenhouse gas emissions by heavy trucks. But for sure there are pros and cons in the real world, and we want to be sure before we are going into the future with such a system. There were a lot of safety concerns in the beginning, so we had to discuss everything with fire brigade and police and so on. We have the voltage level of a tram, and the electromagnetic fields are lower than on a tram, so that isn't an issue. Overtaking is absolutely no problem. You just set the indicator or leave the lane, and the pantograph will automatically drop down immediately, and then you're free to go. So in that part, a battery or the combustion engine will take over, and you will have the full power without interruption.
One of the things that's really obvious sitting here is that the technology works. Like, we're running off grid power now, and it's really, really quiet in here. There are two main uses for big trucks like this. One is last mile delivery, picking up lots of items from warehouses and taking them out to individual shops. Most of that is going to be away from the trunk road network, so e-highway wouldn't work for that. But those trucks tend to take shorter journeys anyway, and they're sitting idle at night, so those could charge at the depot. The other use for big trucks is taking containers from ports to warehouses, or from one depot to another. Almost all of that traffic goes along big trunk roads like this, and that could all be converted to run straight from the grid, with batteries taking a couple of miles to each end. Roll that out, and suddenly you're replacing a lot of diesel.
What you're doing is bringing the electrons to the vehicle in a cable rather than trying to carry them in a box in a battery. It's the most efficient solution, the most efficient use of energy. We think that it's possible for the system to pay for itself. It's possible to set an electricity price sufficiently cheap for the truck operator that the lower costs will pay for the additional costs of the lorry in about a year and a half, something like that. And we think that it's possible to use some of the money that comes back from electricity sales to pay the infrastructure provider in a way which will make that an investment that's fundable by private finance. And we think there is enough money left on top of that to pay a tax to the government to replace fuel tax. Where you've got real difficulties is some of these journeys into really remote parts of the country. And there's a strong case for saying, look, in some of those journeys, let's have a hybrid vehicle. But the majority of the system works very well on very efficient electricity, and you can do it quickly. So I think that's an attractive thing to do if you can.
We've had more than a century to develop delivery infrastructure that's based around combusting fossil fuels, and that's going to end in the next couple of decades. Britain is planning to ban the sale of new petrol and diesel trucks by 2040, which sounds like the far future, but it's actually only 18 years away. The rest of Europe won't be far behind, and building those wires above enough roads could take up most of that time if that's the solution that's chosen. So right now, we know the basic technology does work. That's what's been tested here. But a lot of things that technically work can't be built economically. If we want to keep to that date, then the UK has somewhere around 3 to 5 years to figure out if this is just a gimmick or whether it's worth investing the billions that it'll take to roll this out. Personally, I try not to give predictions about the future, but I wouldn't be too surprised if those wires become part of everyday life on the road in the next couple of decades. If you want to know where you are, you can check on your phone. It listens for signals from whole constellations of satellites in orbit, and by triangulating all those signals and using a lot of maths, it works out where you are and shows you a little dot on a map. But how do the satellites know where they are? There aren't any landmarks in orbit for them to refer to. If satellites are in a high enough orbit, well away from the atmosphere, then they can predict their position. They'll just keep orbiting in about the same path. There's no atmosphere to slow them down. But that's not precise enough. There will be distortions caused by gravity from the sun and moon, or even from mountain ranges down on Earth. So maybe they could use the other satellite signals, like GPS. But if they're all relying on each other, that could steadily drift apart from reality. Maybe they could track the stars or the features down on the Earth, but that's not precise enough either. At some point, something down here on Earth has to look up in the sky and work out the position precisely. And one of those somethings is hidden away in the countryside of southern England. It looks like a regular observatory, but it's not looking at the stars.
We track man-made satellites in various orbits doing various jobs. They all have to have special reflectors on that enables the light to be returned to us. And so we can measure the time of flight, and from the time of flight derive the distance. You send out a very short pulse of laser light. You do that 1,000 times a second. Each of those shots, because you're using such a tiny short pulse of laser, it's 10 picoseconds long, which is about 3 millimeters. That's the limitation on your precision. So each shot is about 3 to 4 millimeters precision.
This station works round the clock whenever the sky's clear. That's why I'm here today. There will be some genuine observations when the clouds break, but right now I'm not actually disrupting anything. But it does look significantly better after dark.
Because it's a laser, it's a very specific wavelength, so you can filter, and that's what lets you work in day and night. The main problem with the atmosphere is the speed of light in a vacuum is a very well-known constant. The speed of light through the atmosphere is variable according to mainly the pressure, but also temperature and humidity. So we measure those things on site as well. There's probably about 35 active stations scattered around the globe, located predominantly in the Northern Hemisphere, which is a slight problem from a science point of view. You'd like them evenly distributed all around the globe. There's a couple in Australia which are really important because they're providing a bulk of the data for the Southern Hemisphere. Ideally, we'd have a more even distribution.
Of course, as the light fades, there's one assumption that we've been working on throughout this video, that the Earth, the ground we're standing on, doesn't move. And that's not strictly true.
In the early days of laser ranging in the 60s, it was the primary method by which they were deriving those early measurements of the drift between us and North America, say. So you can see long-term trends like the ice caps melting and the redistribution of mass from the ice caps to the equator. All the data goes off to international databases from all the sites all around the world. Anyone, any researcher anywhere can go and grab the international data set, the data from us, from Australia, from North America, from China, from Russia, and can use that data to derive the orbits and do the research they need to do.
There's an old saying, God may have made the world, but the Dutch made the Netherlands. This is the Maasland Barrier, and it's one part of the Delta Works, a set of megastructures that hold back the ocean when high seas threaten to flood this country. This is one of the world's largest movable structures, a pair of 210-metre-long gates designed to seal off the main shipping route to Rotterdam port and hold back storm surges. Depending on whose measurements you believe, somewhere between a fifth and a third of the Netherlands sits below sea level. A lot of that reclaimed from the ocean over years through managing marshland and moving earth and pumping water. There are areas of the Netherlands described as former islands, and these gates are part of the enormous system that Dutch engineers built to keep this country dry. And a couple of hours northeast of here is where they learned to do it. This is just one part of the 10 square kilometres of Waterloopbos, and it was built when the only way to simulate water was to use water. It's now a national monument, and nature is taking back these structures, these experiments.
Waterloop means how the flow runs through a system. That is Waterloop in Dutch. Over here we've mostly done what we call model studies. So basically simulating nature at a certain smaller scale. The whole area started more or less after the Second World War, so around 1950, when there was a big demand for model studies related to the Delta Works in the southwest part of the Netherlands. It was for the Delta Works, but we also did many studies all over the world. Studies of the harbour of Libya, harbours in Tunisia, harbours in the Far East, Hong Kong. The main reason for building the Waterloopbos here is that we needed a lot of space for the models because around 1950 all the models were outdoor. And another thing is you need water. Where we are standing here is basically the bottom of the former South Sea. So we are here standing at a level, let's say, -2 or -3 meters below mean sea level. Here we have a natural water drop of about 5 meters. So we just have to open the gate at that part of the wood and the water will flow freely through this area. We are standing in what we call the delta flume, an enormous rectangular box, so to say. And now you see more an artist's impression of this flume with certain sections cut out and placed perpendicular to the original flume wall. In this flume, the studies are related to the design of breakwaters. These breakwaters are enormously costly, in the order of, let's say, 100 million euros. You take a section out of your breakwater and then scale it down to about 1:5 and test it here. I've been in meetings where they fight for every centimeter of the block. Well, if we propose, well, let's say that the block should be 1 meter, they ask, could not be the block 95 centimeters or 96 centimeters or 97 centimeters, because that is money. Each centimeter you can reduce on a block is money. And therefore, this was one of the cash cows of Delta Hydraulics, doing these studies, which are expensive, but still cheap in the design of a big breakwater. At the moment, the Waterloopbos is a kind of tourist attraction, the upcoming of the computer. That's one of the main reasons that this area was left around 2000. We do excursions for tourists to see how we operated the old outdoor models, and this flume is handed over to the Natural Monument Organization about 2 years ago. So although we left the territory in 2000, this flume was still operational for about 50 years because you cannot easily replace this flume to another place.
The Water Act, part of Dutch law, requires the government to maintain flood defences, and it establishes a maximum risk that's allowed. So there are parts of the Netherlands that, in law, it must take a 1 in 10,000 year weather event to flood. The trouble is that the predictions for what 1 in 10,000 years involves keep getting worse. Since they were completed in 1997, the gates of the Maasland Barrier have only been closed in defence twice, but that's going to become more common in future. Flood defences that were researched here were designed to protect the cities and towns that people already lived in, but with those defences in place, people kept building, and the consequences of failure keep growing. The Dutch are going to have to keep making the Netherlands for a long time yet. When you go to a theme park or some adrenaline junkie tourist attraction, you expect it to be safe. Thrilling, sure, but safe. But how can the companies that create those rides test a new one? Say you've got a new invention, like, say, a zip line that goes around corners. There are a few rides sort of like it in the world, but they all use different technologies and work in different ways. There are standards for things that are mass-produced. How do you test something that's one of a kind? You really swing outwards on that, don't you?
We as a company like to invent and break and test stuff, so we've gone through the process of testing other people's stuff to making our own.
Traditionally, zip lines are a cheap amusement ride. They go from point A to point B, and you need to have clear line of sight. They're different from a roller coaster, which is able to go around corners, but has an awful lot of expense in building the infrastructure to hold the rails up. The difference is our product transitions from a wire rope cable into a corner which is rail-based. That allows you to go much further because the zip line can travel kilometres and a corner can provide a lot of entertainment. We have a patent on the technology, so we've got sole use of it. Previously, braking systems were friction-based. Our new system has eddy current brakes. This is a property of materials that occurs when you move a magnet through a conductor. I have in my hand an aluminium channel that acts as the conductor. If I drop a steel mass down this aluminium conductor, as you would expect, it will fall. If I now drop a magnet down this aluminium conductor, eddy current braking will slow it down, and it will fall at a very slow rate. We've captured that and incorporated it into our eddy current brake. That allows you to have no contacting parts, so there are no wear surfaces. So there's no brake dust that's created. The brake is configured such that, regardless of the rider weight and wind conditions and gradient of the corner, you will always fall at a peak velocity, which we have governed. No electronics in there whatsoever. It solely works on springs, centrifugal force, and eddy current braking.
Regulations on rides and attractions differ massively depending on where you are. In some states in the US, for example, the job of checking that a ride is safe is left to the insurance companies who'd have to pay out if there was an accident. The only time the government gets involved is if something has gone so wrong, if a company has been so negligent that there might be criminal charges. Other countries, like New Zealand, are a bit more strict. There is a difference between foreseeable misuse and unforeseeable misuse. If someone gets their phone out on a ride to take a picture and it falls out of their hands and cracks someone's head open underneath, well, you should have seen that coming when you built the ride. Someone was probably going to do that. You should have put a net down. But if someone deliberately breaks the restraint so they can stand up on your roller coaster, that's their own fault. The definitions are deliberately vague in law, though, because it's easier to say that you should do everything reasonable rather than change the law every time someone invents something new.
Most countries have their own national standards, and they are acceptable ways of doing things. They lay out how you should engineer things, how you should test them. It's important to comply with standards. It's also important to show that you've complied with standards so that people can trace what you've done and why through the design process. Generally, when you're doing something new, though, there isn't a standard that you can use to encompass the entire product. So what we do is we actually go out and we look at all the standards and we pick bits from each of the standards that we think are most applicable. When you design a ride, for example, a zipline ride, you work out how fast the person's going to go and how much force they're going to apply to each of the components. If you have a safety factor of 5, you multiply the maximum that the system will see by 5, and you need to design and test to that factor. What we need to do, though, is we try and work out what will go wrong should any part of the system fail. And part of that failure modes and effect analysis is to work out how people could do stupid things, which they will. You look at history, you look at what people have done on ziplines in the past. The main thing is to stay involved right through to seeing the thing being used, spot potential misuses, and mitigate for them.
Oh, here we go. Oh, man, that doesn't look like much from the outside, but when you swing around that corner, it makes a heck of a difference. In the early days of photography, all you had were shades of grey. Every colour on the spectrum, from red to violet, was squashed down by the photographic process. And actually, early photographic film didn't even manage that. It used chemicals that were mostly sensitive to blue light. So if something was bright red, the chemicals would barely react to it. It just looked black on camera. Which is why darkrooms, where the photosensitive film was developed, could be lit with red light without ruining the pictures. It turned out that film like that would also react to X-rays. Now, visible light can pass through some solid objects, as anyone who's ever held their hand up to a light and looked at their veins can tell you, but X-rays with a higher energy and shorter wavelength pass through objects a lot more easily, so the picture doesn't get scattered into a blurry mess. So an X-ray photo takes those short wavelengths and translates them into something that our eyes can see. Unfortunately, that higher energy also means that X-rays are ionizing radiation. They come with a risk of cancer and radiation poisoning. Before that was known, fluoroscopes, which use a constant beam of X-rays, seemed like a great idea. Now they are very carefully controlled. But X-rays aren't just one wavelength. They're also on a spectrum from soft X-rays to hard X-rays. And there's a team here in Christchurch, New Zealand, who are doing something that, in hindsight, seems really obvious. What if you take X-rays at several different frequencies and then translate all those frequencies to different colours?
Part of the light spectrum is the X-ray spectrum. And in there, we've got a range of energy. Sometimes they're called soft and hard X-rays. But the typical medical imaging device doesn't use that information. Sometimes it's used in airport security. They typically have a couple of detectors, layers on top of each other, and they get those crude signals out and then present it to the eye as 2 different colours. But we're actually getting 8 different colours, and we are doing a lot of computer processing before we get a 3D image of what the materials are. So we actually measure, that's bone, that's water, that's fat. We started thinking about it myself in about 2002. The designers of the detector started 10 years before that. It came out of high energy physics, it came out of CERN's research and trying to find the Higgs boson. Equally importantly, they found a much better way of imaging inside humans than they had before. Each photon that comes in, we actually measure the energy of it. If photons come in so fast, it has to do it very, very quickly. The pixels are 110 micron square, so they're size of a hair's breadth, and each one of them is about 3,000 to 4,000 transistors. They're doing a lot of processing. We've only got a 2-dimensional image, so we've actually got to turn that into a 3-dimensional image. and that's called computer tomography. We do a lot of computer processing and produce 3D slices any way through the object. With the resolution we've got to solve tens of billions of equations, and we've got to try and do that very quickly.
The goal is to make it as easy as possible for people to understand. For bone, you'd typically use white because that's what people think is what bone should be. But if you're looking at something like iodine, a solution of iodine is clear. So we typically assign red, and most people in medicine are used to seeing things assigned to different colours. It's a combination of what looks good, what's intuitive, and what's easy to understand. We've got to the point we can now test things in humans, and we're about to start our first clinical trial. The challenges in going from where we were in 2006 on our first mouse to being able to do the first human, we had to move to the human energy range. So the X-rays you need to get through a mouse are much softer, lower energy, and we need to be able to do large areas of detectors so you can actually scan someone in a reasonable time frame. And then there's the data handling issues. Typically, we think of scanning 1 litre of volume giving us about 10 gigabytes of data. Can you actually scan a large object and manage that kind of data? At the moment, our scanner uses about half as many X-rays as a standard CT. But if you think of imaging something like a wrist, which is not radiosensitive, it's not a thyroid gland, it's not a breast gland, the actual dose from a wrist scan is very, very low. Depending on which country you live in, it's the equivalent of several hours to a day or two of background radiation. Most X-ray detectors need to have a certain amount of photons before you can measure them. Otherwise, you're in the electronic noise. Whereas we work at very, very low count rates, and so we can measure the statistical or the quantum noise quite easily. So we can operate at lower doses. Our goal is to keep the dose the same, but provide 10 times as much information.
There are all sorts of different ways of looking inside the body. I'm really excited in the next 6 months. We're going to scan lots of interesting bits like broken arms and gout in the fingers. And maybe in a year's time, start looking at more exciting things like diseases of blocked arteries. We can actually say not just simply there's something absorbing, but whether it is calcium or iodine or fat. If it's an injury, is there a bit of metal in there or whatever? We can answer those questions. And so we've got a great prospect of actually seeing a lot of things that haven't been seen before.
Last video, I was at the Ashton Graybiel Spatial Orientation Lab at Brandeis University, and while I was there, one of the team just casually mentioned that they have an artificial gravity laboratory.
Artificial gravity facility sounds like something out of science fiction, but it's not, and there's very much a reason why I'm keeping my head straight and forward at the moment. This is the artificial gravity facility, otherwise known as the rotating room. So let's do some experiments. This is unscripted. I don't know what's going to happen now, other than things are going very weird when I move my arms.
Okay, so it's a room that rotates. No one has invented science fiction gravity generators yet. But if you have a theoretical spaceship going to Mars and you wanted to generate apparent gravity to keep astronauts healthy, that's what you do. You would spin up the ship and use centrifugal force. And that lab is the research prototype. How do humans deal with a very strange gravitational environment?
The first thing that you should do is try to push yourself off the wall and align your body with the direction of the resultant.
Oh, okay.
Now you're standing upright.
Wow. Can I walk, or is that gonna...
No, don't walk. It's a little dangerous.
It is almost impossible to envision long-duration spaceflight without artificial gravity. The best way to study artificial gravity on Earth is to build a rotating environment. We started designing it in the mid-80s. Ideally, we want to study its effects on the human body, and we want to learn also how to pre-adapt astronauts to the force of artificial gravity. In 99.9%, those will be highly dysfunctional individuals until adapted.
They have NASA standard sick bags for everyone, by the way. I was required to keep one in my back pocket throughout, just in case, because if you tilt your head too fast, your inner ear has no idea what's going on, and things go wrong very quickly.
You now move your arm and try to go as straight as you can.
Oh! Oh, I moved my head.
You shouldn't move your head.
Do you get used to this?
Yeah, you get used to it, yes. You can adapt. Move your arms and try to feel this force that is...
Okay, just to be clear, I'm not putting this on. As far as I'm concerned, the signals I'm giving to my muscles, I'll move my arms forward. And now I'm forcing them. But I'm pushing against a force here.
If you keep going, at some point, you won't feel the force anymore.
Oh, that's weird.
That's weird, right?
That's so weird.
So now you are adapted.
So if I try and do anything else, I haven't adjusted to it. But that specific movement, my body's got used to.
That's right.
Wow.
One way to visualize this force is for me to try and throw a little tennis ball at you. I will throw it straight at you and see what happens, okay?
Whoa! What? I'm struggling to work this out with Fitbit, because in my head, this is a normal reference frame. But it's clear.
We are rotating. And now I'm going to throw it over there, and hopefully it's going to get at you.
Okay.
Are you ready?
Yeah, ready. Yes!
Oh, nice.
Great.
Wow.
All those odd effects are from the Coriolis force. It's not a real force acting on the ball, but it looks like one when you're in that weird rotating environment. have a look at this 360-degree image of the lab. Now, it's a little distorted because it's from a single camera in the middle, but it's close enough. Here's the tricky part. The circumference of a circle is longer the further out you go from the middle. But because everything in that circle is rotating at the same speed once around every 6 seconds, things on the outside have farther to travel. So they're moving at a faster speed than things on the inside. On the outside, we're moving pretty fast, but that camera in the middle is just spinning on the spot. So let's mark the sideways speed that everything is moving at relative to the rest of the world. Green is fast, red is slow. When you throw a ball across that room, it keeps that sideways speed that it had when it left your hand as it travels into slower moving areas of the room. Now, out at the edge, that was fine. It was going the same speed as everything around it, so it looked like it aimed for the center. But by the time it starts to get there, it's a missile flying outwards compared to everything around it. Now, from the outside, that makes sense. After it leaves your hand, the ball just moves in a straight line. From the inside, it looks like there's a force suddenly sending it sideways, and that is the Coriolis force. And it's not something your brain has evolved to deal with.
Now, if you move your arms, you're pretty much fine. Just by moving around, you've been adapting.
That's ridiculous. Thank you so much. I'm going to throw this at you one more time.
The question that lab needs to answer is, can humans adapt to that over time? And if so, how long does it take them to come back down to Earth?
Let's bring this to a stop, Bree.
Abby, can you bring us to 0? Bring your hands down and boom, boom.
I swear, the room is...
Don't move.
Oh, that's weird.
I think we're stopped, so try to swing your arms in front of you.
Oh, I don't like that.
You've been adapted. There are no unusual forces on your arms, but you feel it, right?
Yeah, they're still doing that.
And now you have to readapt.
Thank you so much.
I got an email that said, "Hi, I am from the Spatial Orientation Laboratory at Brandeis University. Would you like to go in our space chair?" Yes, I would.
The lab does like a whole variety of different things. Space research, spatial orientation. How does a person know where they are in space? We also look at artificial gravity. We look at human postural balancing, sensory motor adaptation and processing. We do some sorts of modeling as well. And we've had a history of looking at motion sickness. There's a lot that we don't know about when does spatial disorientation happen and how can we resolve it.
That went wrong, okay.
The first question of this project is, can we recreate essentially what an astronaut would experience, that sort of weak sense of gravitational cues and the spatial disorientation on Earth? And the way we do it is we put people into this beast, this machine, we blindfold them so they can't use their visual system, noise-canceling headphones so they can't use their auditory system. They're just falling to the left and to the right. And because they're tilting relative to gravity, you can use information about how you are relative to gravitational vertical to figure out where you are. And you're getting this information a little bit through your skin as you push against that seat, but a lot through your vestibular system.
And it's so easy to just overcorrect. Yeah, there we go.
If we want to know how the brain works in spaceflight, we need to approximate the whole variety of conditions and forces without limiting it to just one axis. So we started designing a multi-axis rotation and tilt system, which we call Mars. It became operational about 12 years ago. And about 10 years ago, we flew it on the Vomit Comet. It was actually the biggest piece of equipment and the heaviest that they flew.
Okay.
What parabolic flight gives us is the ability to test in close proximity several gravity inertial force environments. I flew a lot in zero-G. I probably have more zero-G time clocked than some astronauts.
So this chair is balanced on a metaphorical knife edge, and my job is to keep it upright, but I can't shift my body weight, and I've got no cues from my eyes or my ears. Instead, all I have is this joystick. And you know what? I don't think I'm doing too badly at this.
Your inner sense of balance is inside your inner ear, and your otolith organs are these little hairs that tell you how much you tilt. In the upright, those hairs tilt the more you deflect, and you have a good sense of where you are. When you're on your back, the only thing that you really have through your canals and even through your skin is velocity. So I take the people and I tilt them until they're on their back. And because they're not tilting relative to gravity anymore, you can't really use gravitational cues to figure out where you are, and people become wicked spatial disoriented.
Whoa, okay.
You know, I put pilots inside there, they don't know where they are. 90% of people have no idea. One of the core things I was very interested in was, how do people learn over time? People in the upright who have a good sense of where they are, I was curious, well, what does learning look like even in that condition? Because no one had even looked at that. And so we took data and we 3D printed each of the trials. So this is trial 1, and this is going all the way up to trial 20. And if you have huge circles, that means you're really bad. And as time goes by, people learn. In the beginning, people come in and they're stressed out, you know, and what they do is they grasp that joystick and they are just doing these crazy maneuvers, thinking that they need to respond to every small thing. Pretty rapidly, people are able to learn to do this task. This is our spaceflight analog task. This is when you're on your back. You don't have gravitational cues that tell you about your angular position. It is just a mess. People are in for 40 minutes and very, very minimal learning. There are some small things that they learn, And that's what I use to create a training program that's actually effective. And these red marks here are destabilizing joystick deflections. This is when you make a deflection of the joystick that actually throws you away from the balance point because you're kind of disoriented.
Did I just steer into the fall?
Based on what I've been looking at, there are really 2 times that this happens. One is just some weird freak thing where they're just like, and who knows why that happens? We need to study more. We want to do imaging and things like that. But the second time it happens is timing. People are doing this joystick deflection and they sort of hold on to the joystick a little too long, and that becomes destabilizing.
This is impossible.
I look at learning. I look at how do you create effective training programs, and I also look at, can we do technological countermeasures that can help people in that condition?
Thank you to all the team at the Spatial Orientation Laboratory at Brandeis University. Pull down the description for more about them and their work. That is genuinely... I work with computers and digital video a lot, which means that I think of colour in terms of light, in terms of amounts of red, green and blue. Someone who works with print might think of colour in terms of combining inks, cyan, magenta, yellow and black. A physicist might think in terms of the frequencies and wavelengths of the light. But there is a very different way to look at it, through the chemistry and compounds that make up colours. Inside those buildings, the Harvard Art Museums, is the Forbes Pigment Collection.
The pigment collection was put together by Edward Forbes, who was the second director of the museum. He'd been buying works of art, and in doing so, he discovered that the dealers in Italy were seeing American collectors as something of a mark. What he decided is that if you understand what a work of art is made of, what the original materials were that an artist used, then you can tell original from restoration, original from fake. And so what he did was start buying pigments to use as standards for the analysis of works of art. Knowing that it was visible to the public meant that I needed to make some sense of what we have as a collection. So what I did was take a colour wheel, open it out, have yellow in the centre, and we go along one way to blue, along the other way to red, and purple at each end. So we have unique colours along the top. We have duplicates of those colours, which are chemical duplicates, but not actual colour duplicates. And then underneath on the bottom shelf, we have the raw material that makes up the colours above. In effect, what we have are the materials that make up paint next to each other. And then if people look at the galleries below, they can actually see what artists can do with these raw materials. If you think about iron oxide, for example, hematite, but as it forms in the earth, those slight additions that the earth adds into the hematite deposits that allow it to look slightly different. So we have 60 different samples of hematite. Each of those is a slightly different shade from the other. These pigments are not used for restoration. We use them only as standards for analysing samples from works of art. By analysing the materials, we can understand the thinking process, and if the artist is no longer alive, it's really the closest way to having an interview with the artist. It's also great for teaching. We can show the students how pigments change. They not just fade, but some pigments darken. So it's like Vaseline, but 80 years old. It doesn't last forever. Vermilion, red lead will turn black on exposure to light. You can see how it started. And then other pigments like eosin, which Van Gogh used a lot, will fade and give an entirely different impression of what the painting was to what it looks like now. And so for security, we don't have the public in here. Some of the pigments are toxic, so we don't want people touching them, playing with them. So pigments are made of mercury, they're made of cadmium, arsenic, and so on. The oldest white pigment is lead white. It's made by taking lead metal, putting it into a container with vinegar. That container is buried in cow dung. So out of manure, you get the most pure, beautiful white pigment. That's been around for hundreds and hundreds of years. People use it as makeup. Lead white is toxic in the way that lead is toxic. We have mummy brown. It has been used probably since the 17th century, and it's made up of Egyptian mummies that have been ground up into pigment. Indian yellow is an interesting pigment. It's made by feeding cows mango leaves only and collecting their urine and drying their urine. What you see on the screen depends on the limitations of what the computer screen can depict. So videoing them, putting them into the digital format doesn't replicate the colour. There is innovation and people are developing new ways to depict colours. So, for example, Masu Romanian developed a blue pigment called Yin Min Blue. He discovered it by accident. It's very stable. And it's the first inorganic blue pigment that's been invented for a couple of hundred years. There's been a new black that's come onto the market, which is Vanta Black, which stands for vertically arranged nanotube arrays. What you have is a forest of very tiny tubes, and light will go into that. It will bounce around inside the tubes and then get issued as heat. It's a beautiful velvety looking surface that doesn't bounce any light back. Chemists produce more and more pigments every year. And I think that we're going to see pigments depicting colours that we never thought were possible. Every day somebody is coming in here, taking a pigment out and using that as a reference. This was beautifully arranged when I installed it. It took me like 4 months of lining everything up. And it's all a little higgledy-piggledy now, so you can tell that we use it all the time. It's not an historic artefact, it's something that we rely on to do our work properly.
The final guest video in this run is from Ali and Micah, a neuroscientist and a clinical therapist who run neurotransmissions. Their video has giant magnets, 3D printing, and a Star Wars action figure. Ali, Micah, it's all yours.
We're here at the Keck Center at UC San Diego, and this is a functional magnetic resonance imager, or an fMRI?
Well, functional, but not functioning. This is actually a dummy scanner that's used for educational and training purposes. An actual fMRI machine houses a 3 Tesla magnet that's more than 60,000 times more powerful than the Earth's magnetic field, and over 3,000 times more powerful than your average fridge magnet. If we were anywhere near the real deal, well, we would put our camera and our equipment at serious risk.
But why on earth would anyone possibly need a magnet so powerful? Well, some of the researchers here at UCSD are using fMRI to study the human brain in ways that 30 years ago just weren't even possible.
I'm Maggie. I'm a 4th year graduate student at UC San Diego.
My name is Stephanie Nelly. I'm a 6th year PhD student in John Serens's lab.
We study mostly selective attention and expectation and other cognitive factors and how they influence visual processing in humans.
My research is about really basic visual perception. How do we make sense of the world around us? How do we choose out of the plethora of things that are constantly kind of accosting our visual system? How does your brain kind of make sense of the massive amount of information constantly bombarding it? fMRI itself was developed not very long ago. It's a very new technique as far as human research goes. And it was developed in the 90s, I believe, actually at Bell Labs.
fMRI is a particular specialty of MRI called functional MRI. So what that does is basically, instead of measuring the difference between particular tissues, you're actually optimizing to detect the difference between oxygenated versus deoxygenated blood in a person's brain.
For a long time, it was impossible to look at the brain up close without cracking open someone's skull. And even if you got a brain from someone who's passed on, that's not all that useful for understanding how it works. When Leonardo da Vinci dissected the human brain in the 16th century, it was with the intention of finding the seat of the human soul. Spoiler alert, he didn't.
Unsurprisingly, the functions of different brain areas were essentially a mystery well after the scientific revolution. But fMRI changed all of that by giving scientists the ability to see the brain working in real time, track activities in different brain regions, and read your mind.
No, unfortunately not for us scientists. An fMRI machine cannot read the mind. It can tell you basically where blood is being transported to in the brain, so which parts of the brain are active.
An fMRI scan can tell you when someone is doing some cognitive task, what kind of patterns of brain activity you see. So which areas are active, what information are those areas representing. For instance, if you have someone look at different images and you measure MRI while they do that, then later if you have that same person come in and you say, okay, think about something, now I can, based on that information, I can guess what you were thinking about.
I could probably say you're looking to the left by looking at your neural activity. Or I could say you're looking at a horizontal line by looking at your neural activity. However, am I going to be able to tell what you're daydreaming about or who you're in love with or something like that? No, I don't think that's going to happen in my lifetime, but, you know, set it on camera so we'll be able to.
It might not quite make sense how a magnet does all of this, so let's break down the process step by step. Let's say that Ray here has been having some neurologically linked problems and a doctor refers her for an fMRI.
The technicians place her on the table, give her some earplugs, and stabilize her head so she can't move it at all. If the head moves during the scan, the images will come out fuzzy. Next, the table slides into this large donut-shaped section, which houses the ultra-powerful magnet. The strong magnetic field of this magnet then actually turns the hydrogen atoms in our blood.
Wait, what?
Yeah, the human body has a lot of hydrogen atoms because, well, we're mostly made up of H2O. That's water. The magnetic field from the fMRI interacts with the protons in the hydrogen atoms and makes those protons essentially point in the same direction. That's right, your molecules are magnetic. Hence, the magnetic resonance part of magnetic resonance imaging.
Once Ray's in position, she'll hear a series of very loud clangs and beeps. But these sounds aren't just the hottest new beat. They actually serve a purpose. Every clang you hear is a radio wave pulse being fired off. This radio wave disrupts the uniform direction of the protons and pushes them in slightly different directions. Here's the cool part. As the protons move back into realignment, they release their very own small radio signal. And those signals are then detected by the fMRI machine's radio receiver, which starts taking snapshots of cross-sections of your brain, which you hear as the beeping sound. After some complicated computation, what shows up on the computer screen is a series of images that show both the anatomy of your brain and highlighted areas where there's more blood flow. Pretty cool, right?
Yeah. So fMRI doesn't actually measure your brain activity. It can't detect your individual neurons firing, as cool as that would be. fMRI machines actually detect what's called the BOLD signal.
So the BOLD signal stands for blood oxygen level dependent signal, and it's basically an index of how much oxygenated hemoglobin is in a person's blood at a particular point in their brain.
Neurons themselves don't keep a high, store of glucose hanging around so that they can do their job. And so the blood vessels through these things called astrocytes actually help supply neurons with the glucose and oxygen that they need to do their signaling.
When you have neural activity that happens in your brain, a bunch of blood will rush to that area, and it turns out that oxygenated and deoxygenated hemoglobin in your blood blood have different magnetic properties. So deoxygenated hemoglobin will kind of disrupt the magnetic field more than oxygenated hemoglobin will, and it'll actually cause a decrease in the signal. So when you look at an fMRI image, the higher the signal you have, the more oxygen is in your blood at that point. And so you actually can measure the bold signal after these neural events occur. That basically tells you how much energy was consumed at that location.
Now, it's not perfect. Like, it can't detect changes instantaneously or tell you exactly what kinds of signals are being sent.
But even with its limitations, it lets us better understand which brain regions do what. Using fMRI, scientists have been able to identify 180 distinct brain regions. Better understanding the roles of different brain regions means that doctors can use that information to help treat and support patients with neurological disorders or brain injuries.
fMRI technology is cool, but both of us wanted more. We wanted to get into the machine and see what our own brains looked like. Maggie and Steph asked me to participate in a pilot research study looking at how humans distinguish between faces, and I jumped at the chance to help out.
I didn't participate in the study, but I was able to get a structural scan. It doesn't measure blood flow, but it does give you a high-resolution image of your brain's anatomy. It was a strange experience being inside. It felt like being in a plastic coffin. I can see why some people get claustrophobic.
And participating in the study was harder than I expected. While the task I was doing was easy, it was hard to stay focused on doing the same thing over and over for almost 2 hours. But it was also really cool to see the results.
And yet, we could not pass up on the opportunity of a lifetime.
I mean, sure, it's cool to see your brain on a screen, but imagine holding it in your hands. What does my own unique brain really look like? Well, as it turns out, we're able to find out.
Thanks to modern software, we're able to take the 2D slices of our brains and compose them into a 3D render and print them out. Cue the time lapse. Look at that beautiful brain.
I really liked how the rainbow filament turned out on
Yeah,
this.
it's so
This
pretty.
turned out really cool.
I know, and I really like my glow-in-the-dark print. It's like super bright.
The grooves are much wider in yours and like not quite as tightly packed, whereas mine is like super tightly folded.
It's cool that you can see the inside too, like the hippocampus and all
Yeah.
these different brain regions.
Obviously, I knew that my brain wasn't perfectly symmetrical. No one's brain is, but you can really see like very obvious differences. It's really interesting to see like, oh, that's my brain's shape.
Right. I didn't really think about that before.
Every time someone comes over to our house, they'll be like, "Did you see my brain?
Let me show you my brain.
Let me show you my brain."
It's incredible that we have the technology to track the activity of a live human brain. fMRI has pushed neuroscience to new heights and has given us a glimpse into the seat of human consciousness. And only somewhat less incredible is the fact that we can use those same images to build 3D models so we can create a life-size version of our own brains. How funny that just a chunk of squishy cells this big can come up with such incredible tools to help us better understand our minds and ourselves.
Huge thanks to Maggie and Steph from the Sorensis Lab for their expertise, and to UCSD for giving us access to their scanner. And thanks to Tom for giving nerds like us the chance to share our brainy love. Maybe we'll see you later?
Maybe.
Until next time, we're Neurotransmissions. Over and out.
Thank you, folks. Go subscribe to Neurotransmissions. I would recommend starting with Micah's video on training a cat to high five, or Ali's video on how marijuana affects your brain. And that's it. I'm back next week, and I will see you then. A lot of modern cars come with advanced driver assistance systems. Things like adaptive cruise control that keeps a safe distance from the car in front, or automated emergency braking to avoid collisions, or lane assist to keep you in lane, which is great as long as the driver knows the system's limits. The worst modern car I've ever driven came with adaptive cruise control that turned itself off if you went under 20 miles an hour. So if the car in front slowed down for a traffic jam, so would you until you went under 20, at which point the car just handed control off to you with a very quiet beep. And if you weren't expecting that... This is the Global Vehicle Target, and as of this year, it is part of the Euro NCAP standard on how to test the safety of automated driving systems. But it isn't just a static foam model. This base here is a robot platform that goes up to 50 miles an hour, which means you can test safely with both vehicles going at highway speed. Right, my turn in the passenger seat. I mean, of the real car, not this. This doesn't have a passenger seat.
Thatcham Research is a not-for-profit, insurance-funded research centre. In about 2014, it became clear that the next generation of technologies weren't just going to look for the rear end of the car, they were going to look at the side of the car and even the front of the car. We've got to have a target that actually looks like a three-dimensional car. The impactable bit, the visual pieces of the car, are actually foam target blocks that are assembled to look like a car and covered with a radar material. Generally, you can put the target from start back together in about 15 to 20 minutes. But what we've done is we've used test equipment that actually measures the the radar reflectivity of a real vehicle. You get radar reflectivity of a wheel, and even the glass at the back of a vehicle has a certain radar signature. So it's about putting radar reflectors, but also radar absorbent material in the right place. So the brand new tests that we're going to introduce in 2020 are what we call turn across path, where your vehicle is moving in front of another vehicle, and we want your vehicle to brake. We're also developing junction tests where a vehicle moves across your path laterally, and therefore we need to see the side of the vehicle. And we're confident that if a vehicle brakes for our target, it will brake for a real vehicle in the real world.
This should stop in time.
Yes.
Yeah. Okay. All right, let's do it. Oh! First of all, that worked. That's good.
We have stopped.
Oh, that made me feel so nervous.
It's deliberately late and harsh.
Radars are very good at understanding if something is moving, they can identify what it is. However, if you just come across an object and it's stationary, it's much harder for the radar to identify that that's a vehicle. What's the difficulty is understanding, has the driver seen it, and what are the driver intentions? So if you've got a vehicle that's parked in front of you, it doesn't want to warn you too early because that's going to annoy the driver. And we don't want that because if your driver is annoyed, he'll turn the system off. One of the problems vehicle manufacturers have is there are not only differences in the road infrastructure, but there's actually national characteristics. People in Germany tend to drive slightly more aggressively, and therefore the issue of false positives is much more of an issue. Whereas the Swedes will tell you that they're much more benign, and therefore a vehicle that's just stationary, warning the driver won't really annoy him too much.
Okay, so what happens if we go slightly faster?
Well, we'll try it. It should be good. We'll do 40 miles an hour rather than 30.
All right. Oh, I don't like this. I really don't like this. Oh! Does it slightly brake to warn you?
Yes.
Yes.
You hope is that little brake is enough for the driver to go, oh, this is something strange is happening, and do it themselves.
Okay. Yeah, that works. So's a target.
Yeah.
Thank you very much to all the team at Thatcham Research. Pull down the description for more about them and their work. A nuclear reactor run by undergraduate students at a liberal arts college sounds like an interesting idea, but it's real, and it's been here at Reed College in Portland, Oregon for 50 years. And yeah, we're going to put a camera in it. Go for it.
The Reed Research Reactor is a trigger reactor designed to be operated by students and designed to be used as a training reactor. We got it because we had a radio chemist on Reed's faculty. He thought that it'd be really important for students to have access to this cutting edge technology that was nuclear reactors. So we have a tank that's 25 feet deep. It's full of around 25,000 gallons of water. We think that we have enough uranium to continue operating at our current rate for 100 years without having to change it out. We operate at 250 kilowatts, which is actually a pretty low power. While it does produce power when it operates, there's no way of harnessing that to make electricity. The main purpose of our reactor is for science.
The kind of research we do is called neutron activation analysis, and the logic behind it is if you don't know exactly what something is made out of, you can make it radioactive and then find exactly what it's made out of and then like work backwards and figure out what it was originally and then let it sit in a room until it decays and then you have your original thing back. You can put 80 things in there, you drop it into a tube, and then you turn it and it turns and it gets the same amount of neutron exposure, and then we get it out with a fishing rod. And then afterwards, you have to be very careful with it because it's contaminated. The water at the bottom of the reactor becomes radioactive. It has N16 in it, nitrogen-16, but because N16 has like a half-life of 7 seconds, when the water is cycling through, it gets diffused through a nozzle, which causes the new water to like swirl around like this, which makes the delivery time from the water at the bottom of the reactor to the water at the top of the reactor just like a few seconds longer than it needs to be. So water at the top isn't radioactive, and that's one of the coolest parts about our water system.
The radiation levels that the reactor produces is actually very low, but the water provides sufficient shielding, so it's safe for us to be in here while the reactor is operating. It's a very small reactor. It doesn't get hot enough to melt down. It doesn't explode. So the way we shut down a reactor in an emergency is with something called a scram. So we have a special button. It's labeled the scram button. And when you press it, it cuts power to those electromagnets and it automatically shuts the reactor down. If someone drops their phone or some other object into the pool, normally what we do is we get a bucket on some string and we try to scrape the object into the bucket with a very long stick. Or we wrap duct tape around heavy weights and we lower the weight into the pool on a string and try to pick it up that way. We have a pretty good success rate.
Should we turn the lights off so we can see the blue glow? Wow, that looks awesome. The blue glow is Cherenkov radiation, which is a bit like the visual equivalent of a sonic boom, but there are other people much better qualified to explain that than I am. Research reactors aren't very common, but there are more than you might think. There are a couple of dozen in the United States alone at universities and research institutes and a few companies. This one is basically a student society, just a student society with a lot of regulation and oversight.
So before you're allowed to operate the reactor, you have to get a license from the U.S. Nuclear Regulatory Commission. Our students train for an academic year before they sit down for that exam. You have to do things such as memorize diagrams for our cooling system or our ventilation system. You need to be able to explain how the physics work, how to protect yourself from radiation, and how to actually use controls of the reactor. We license 15 students to operate every year. Currently, we have 30 to 40 students on staff.
You don't get academic credit for working in the reactor, and I think part of that is because we get paid to work here because this is a job. This is the reason why I came to Reed. I just thought it was really cool that this was a facility that existed at a school, and I was like, I'm going to do that. When I first started the training program, I had to pull aside the training supervisors and say, like, you have to explain the atom to me from the beginning because I don't know anything. I worked really hard and I just really wanted to know it. Now I know it and I still think it's really cool and I get to both ways to like operate this.
I'm looking at a nuclear reactor. Oh, wow. I've never actually seen Cherenkov radiation in person before. It's amazing. I'm in Toronto, Canada, and Toronto is cold for a lot of the year. Good winter boots are a necessity. They've got to be warm, they've got to be waterproof, but also they've got to stop you going arse over apex when you suddenly walk on a patch of ice. This is Winter Lab, and it's part of the challenging environment assessment laboratories at the Toronto Rehabilitation Institute, and this is their tilting frozen floor.
If you want to find out whether people are at risk of falling, at risk of a road accident, at risk of something, you need to put them in a challenging environment and see how they respond. What we have is 4 modules for different things. We have the world's actually most realistic driving simulator now. When it rains in our simulator, it actually rains. We also have Stair Lab, where we have people walk up and down stairs, and we suddenly and unexpectedly move the room, and they have to grab the handrails, and we can see how effective the handrails are or the stair design. 21,000 people in Ontario every winter on average end up in our emergency rooms because they've fallen on ice and snow. So the purpose of Winter Lab is so that we can do 2 things. One is that we can test the boots and inform consumers what they should buy, and the other is we can help companies and ourselves develop better boots.
I know I'm harnessed in, but that is terrifying.
It's an ice box, really. It's insulated. We can generate winds. We can actually make nice white fluffy snow. We can control the air temperature very precisely, and we can control the temperature of the ice very precisely. We actually have a group of graduate students, like every other university lab you've ever been to, because they're not very expensive and they're sort of disposable, who do this testing because we want sort of uniformity.
It's a good harness. Very good harness.
Now, in order to test the performance of shoes, we choose to put Winter Lab on top of a platform that we can gradually tip.
It does feel ever so slightly like gravity is shifting.
We tip it as you walk up and down until the moment that you slip. We have an angle which we think is just acceptable. It's 7 degrees. We actually take the minimum value of several people. If you can make 7 degrees up and down confidently, we give you 1 snowflake.
This is a good shoes. I can just... Oh, okay, yeah. No, I can literally just walk normally.
At the moment, we've got a scale of 3 snowflakes. And that was because the first time we ever did this, 90 out of 100 boots failed to get 1 snowflake, and nothing got better than 1 snowflake. So to publish it as a 5 snowflake scale looked a bit depressing. We've already tested some prototypes for next year, and they're getting 2 and 3 snowflakes.
But that's fine. I put my foot down. It just stays where it is.
We are really quite confident that eventually we're going to be able to add some more snowflakes at the 4 and 5 level. It raises another interesting point, and that is, can you have too much friction? We're a long way off that yet, but of course, more than half the falls that you experience are people tripping up. We will eventually decide whether a 5 snowflake shoe is a good idea or not. I'm really happy. In 2 years, we've done 2 things. One is that we've changed the buying habits of people, and the other is now the industry is improving the quality of boots, and we're helping them do that.
Thank you very much to all the team at Winter Lab here at the Toronto Rehabilitation Institute. Pull down the links in the description for more about them and their research. I swear. This is the Royal Air Force Training Centrifuge at Farnborough, and the team here are going to push me as far as they are allowed to push a civilian.
The centrifuge has been here since 1955. The device was originally installed for research purposes, although these days it's used for training as much as it is for research. And what it does is recreate the forces that you feel in an aircraft. For our routine pilot training, the first time pilots go on the centrifuge, we expect them to get up to 5G without a G suit and then up to 7G with an anti-G suit.
Now, I'm not taking a significant risk here. I'm healthy, I've pulled a few Gs before, and the human body can take this. And the reason we know that is because in the 1950s, the US Air Force used rocket sleds to push volunteers to incredible speeds. But that rocket-powered acceleration wasn't the dangerous or even the really high G part of the test. See, high G acceleration takes a lot of incredibly expensive rockets or a big old centrifuge like this. But high G deceleration, all you need for that is a wall. Or for something less destructive, like the rocket sleds, you use scoops dropped down into a water trough. US Air Flight Surgeon John Stapp, aboard the rocket sled Sonic Wind #1, holds the record for the highest sustained G-force anyone has ever voluntarily endured, 25 G for 1.1 seconds, with a brief peak over 46 G. And he was badly injured, but he survived and he recovered, and he lived to the age of 89. The human body is an incredible thing, particularly because we didn't evolve for this.
G tolerance is something that's innate in all of us. Some of us have high G tolerance, some of us have low G tolerance. Over the years, people's G tolerance doesn't really adapt. Any shortfall in G tolerance has really got to be made up by physical exertion in the G-straining manoeuvre.
What this centrifuge doesn't have is much jerk. And jerk is a technical term. In the same way that acceleration is the rate of change of speed, jerk is the rate of change of acceleration. And because it takes time to spin up and spin down, oh, here we go,
Even though the acceleration is high, the jerk here is relatively low, about 1 g per second. Jerk is the difference between a rocket to space, which might take a couple of minutes to reach peak acceleration, and a fighter jet, where manoeuvres might change the g-force acting on you in a fraction of a second. And it can go further than that. You can measure the rate of change of jerk, which is called snap, or jumps. The two derivatives after that are called crackle and pop, but they're not all that useful in the real world.
As we increase the G that Tom is exposed to, the blood's going to be pushed down into his feet, and he's going to have to work really hard to push that blood back up to feed oxygen to his brain to keep him conscious. And in real life, we would be expecting that person to be flying an aircraft whilst doing that.
I'm getting a little bit of grey out, I can't quite see.
We teach the anti-G straining manoeuvre, which composes of 2 separate parts. First of all, muscle tensing, so both the buttocks and the legs, squeezing the blood vessels to try and get the blood back up into the chest and the head. But also the second part is a breathing manoeuvre, which increases the strain in the chest, directly increasing the blood pressure to the great vessels in the chest and keeping him conscious. And when you lose blood pressure to your head, you could even lose consciousness, and we term that G-induced loss of consciousness, or G-lock.
Blimey, I lost everything there. Wow.
G-lock in itself is not dangerous, but the real point is when you G-lock, you're flying an aircraft. So if you're not able to fly that aircraft, I'm sure you can appreciate that that is a real problem.
Because of John Stapp and all the volunteers like him that rode the rocket sleds, there is a lot of research into acceleration on the human body. How many Gs can be withstood for minutes at a time? How many Gs can be withstood for brief moments? And how many can be withstood with training that I clearly don't have? Rocket scientists and roller coaster designers use that data. But there's not much research into jerk, because how do you test it without also testing acceleration? I'm at Vichert's Earthquake Observatory in Göttingen, Germany. This is the oldest working seismic station, earthquake detector, in the world. But there's also a more unusual bit of scientific equipment here, a 4-ton steel ball that can be raised up 14 metres above the ground and then dropped. Because it's a lot easier to set up and calibrate an earthquake detector if you can make the ground shake yourself.
The equipment we have here started to work 1903, and it's still working. Vichert was the one who created the first real working seismometer. These things record on smoked paper. This is ordinary white paper. We take the flame of a paraffin burner to get soot onto that paper. We think we are the only ones in the world who are doing that. Vichert had a theory that seismic waves allow you to look into the inner of our planet. His assistant, Mintrop, had to prove Vichert's theory. He started to calculate, and he found out if he takes a ball of about 4 tons and drops it down, he is creating a small earthquake. An earthquake big enough to check the theory of Emil Vichert.
The researchers here, a century ago, could create a tiny artificial earthquake and then measure it. So what? Well, earth tremors move through the ground in 2 ways. The P waves, or primary waves, compress the ground back and forth in the direction that the wave is travelling, squeezing it together. Travelling slightly slower are the S waves, the secondary waves, which shear the ground side to side. And those waves behave differently in duration and wavelength and intensity, depending on the ground they're travelling through. So, if you're clever, and Mintrop was clever, then you could set up seismic detectors all round an area, create a small artificial earthquake by, say, dropping a 4-ton steel ball, and use the reflections from within the earth to build up a picture of what was below without having to dig.
This knowledge spread all over the world. Mintrop got an invitation to Mexico from an oil drilling company. They had an oil field. They asked Mintrop if he could measure the size of that oil field. He said, I don't know. We don't have oil fields in Göttingen. But he accepted the invitation to Mexico, and of course he did not take the ball with him, because in Mexico he wasn't allowed here. He was allowed to use dynamite. And he measured the size of this oil field with an incredible accuracy. He had the not so nice nickname, the Crazy German. He was running around with bodyguards, hiding his equipment in tents, because our American friends were very eager to find out how that works, because that was the license to print money.
So, 100 years ago, with a much older release mechanism and probably a lot more effort, that steel ball dropped for the first time onto what was then pretty much flat ground. Nowadays, there's much better equipment for figuring out what's under the Earth's surface, but it's not quite as dramatic. It's still rolling.
Hi, I'm Jenny. And I'm Melissa. And we're here underneath the University of Arizona's football stadium in the Richard F. Harris Mirror Lab. Behind me is the world's largest spinning furnace filled with 38,000 pounds of molten glass.
Over the next couple months, the glass will slowly cool and start to form a mirror, one of 7 that'll be part of the Giant Magellan Telescope. Once completed, the GMT will be the largest telescope in the world. The GMT is being built in Chile at the Las Campanas Observatory in the Atacama Desert, and it's scheduled to see first light in 2022. This massive telescope will have 10 times the resolution of the Hubble Space Telescope and more than 7 times the light-gathering power of the largest telescopes today. The GMT is made of 7 8.5-meter mirrors for a total diameter of 25 meters, and it will be used to study galaxies, stars, and exoplanets.
The GMT-5, which is the mirror being cast right now, is actually the 20th mirror made at this facility. Other mirrors have been made for other telescopes, like the MMT, the Large Synoptic Survey Telescope, the Twin Magellan Telescopes, and the Large Binocular Telescope. It was built under the stadium to take advantage of the large columns which act as load-bearing structures for all the heavy equipment needed. It's also nice and quiet when there aren't football games going on. It's a great way to make football benefit both the university and science.
To start off, we need 38,540 pounds of glass. Sand is shipped from all over the world and brought to Japan, to the Ohara Glass Factory. They're the only factory in the world that can make the E6 low-expansion glass that's needed for the GMT mirrors. The glass is made in 2,000-pound batches made exclusively for the University of Arizona. It takes around 2.5 years to make enough glass for a single mirror, so, plan ahead.
The glass is then shipped here to Tucson. Once the mirror lab gets it, they have to clean it, inspect it, and weigh it. If there are any stresses or imperfections in the glass, then the piece is rejected and made into paperweights.
Each individual piece of glass is placed carefully into the mold and inside the oven. The 40-foot diameter oven is then gradually heated to a temperature of 1,350 degrees Fahrenheit over the course of a week. There are cameras in the oven to monitor the process, but once it begins, there's no turning back. At this point, the massive oven is filled with 19 tons of glass and starts to spin 5 revolutions per minute. Once the oven reaches 2,129 degrees Fahrenheit, or 1,165 degrees Celsius, the consistency of the glass is about the same as honey and starts to flow into the mold.
It might make sense why we need an oven to melt the glass, but you might be wondering, why does it spin?
It spins to make the shape we need for a mirror, a parabola. Modern telescopes use parabolic mirrors to collect and concentrate light. They use the parabolic shape to get the light into a central focus point. And the bigger the mirror, the more light is collected.
But what does this have to do with spinning besides making us dizzy? Well, let's take a look. So it turns out that spinning a liquid actually causes it to automatically become this parabolic shape. So whenever you spin the glass, it creates the perfect shape needed for a mirror. This is a massive improvement over how mirrors used to be made, and it grinds years off the process. The mirror spends 3 months cooling and annealing in the oven. So now it's the right shape, but it isn't quite done yet. When light hits the mirror, the surface has to be smoother than a fraction of the wavelength of light. Otherwise, the image is distorted. In order to get it this smooth, the mirror lab spends 2 years polishing the glass. It has to be smooth to the point where no imperfection on the surface is larger than a virus. After all that, after melting the glass in this giant oven and polishing it for 2 years, all you have is a huge, really smooth piece of glass.
So the mirror lab actually doesn't make any mirrors.
The final step in turning this giant piece of glass into a mirror is actually done on site at the observatory. A layer of aluminum about 100 nanometers thick is deposited onto the surface. To cover a mirror of this size, it actually only takes a soda can's worth of metal.
Unlike your mirrors at home, the reflective coating is only on the front surface, so it's very delicate and needs to be re-illuminized every so many years.
Thank you to everyone here at the Richard F. Karras Mirror Lab and the Stewart Observatory. Tours are open to the public every day of the week.
5, 3, 2, 1, go.
I'm experiencing 1.8 Gs right now, which means I weigh about 1.8 times what I normally would. I've been instructed to keep my head front and centre to avoid nausea. But all this is about to change because this is the European Space Agency's zero-G flight. Those are students doing research. This is Neil, who's here for my safety. And we're about to go into free fall. Whoa! Whoa! And here's the confusing thing. We are still going up right now. That camera is stabilized to the actual horizon. And it's not until 10 seconds into our 20-second parabola, into our maneuver, that we clip the apex and start heading back down towards the ground. And here we go, 1.8 Gs. Oh.
In this special aircraft, we divide the 3 axes, pitch, roll, and thrust, and each pilot fly 1 axis. So in every other aircraft, one pilot flies the 3 axes and the other one manages the system, talk to the radio, and so on. To fly parabolas, we need to fly only 1 axis by 1 pilot. We try to avoid any turbulence. Every turbulence is a nightmare for us.
The 2 control sticks, just like any plane, are completely locked together, so they always move at the same time. So one of the pilots is using effectively elastic bands on either side of his stick so that he doesn't affect the axis of the other pilot. One of them does the pitch, the other one does the roll, whilst trying not to upset the pitch.
In 1971, the Apollo 15 astronauts tested something on the moon. The idea that all objects, no matter their weight, fall at the same speed if there's no air. They used a hammer and a feather, and they landed at the same time. But the weird thing is that if an astronaut had thrown that hammer, it would still have been in freefall from the moment it left his glove to the moment it hit the ground. The only pull on it is from the gravity of the moon. The maths work out the same no matter what speed or direction it's going relative to us. That's what we just did here. If it sounds weird, sure, but we just proved it. We're about to prove it again.
Every 5 parabolas or 10 parabolas, we change to maintain the best accuracy of the parabolas, especially on the pitch axis, because it's the most demanding flying techniques. So after 5 or 10 parabolas, you are so tired and you have to go on another less demanding axis.
3, 2, 1, go.
This parabolic maneuver isn't the normal kind of thing that you do in an Airbus, and the software in this plane hasn't been modified, because to do so would be a huge effort to requalify it. So with the normal software, you have the normal alarm saying, this doesn't seem like a very good idea, guys. And one of the pilots that isn't too busy on the other 2 axes is turning off the alarms that we don't need to worry about and keeping track of the ones that we might need to worry about.
So those pilots are keeping us on the exact path that an object would take if you hurled it into the sky at hundreds of kilometers an hour and there was no air. They're giving us this little protected bubble of 0G to fly around in. There is no terminal velocity here, only the design limitations of the plane, and we're going to hit those pretty soon, along with something else, because when you're descending this fast towards the ground, the Earth approaches pretty quickly. Thank you, Neil. If you're a master's or PhD student from an ESA member state and you want to be one of the people back there, then have a look at the Fly Your Thesis program. The link is in the description. Thank you, Neil. I got it, we're good. And down. Oh! I'm in the National Advanced Driving Simulator at the University of Iowa. It's used to test drivers' reactions in a controlled, repeatable environment, and also to test things that would be unsafe in the real world.
Tom's currently in the simulator, undergoing a study to look at driver response to unintended acceleration. The vehicle is going to accelerate quickly without any input from Tom, as if it were malfunctioning. Tom's going to have to identify that this event is going on and press the brake very quickly to bring the car under control.
Turn left at the next intersection.
Whoa, 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 whoa. That was terrifying. But there's a question I want to answer here. Recently, I did a video while driving, and it was on a dead straight road with very little traffic, and I always felt in control of the vehicle, but was I? Is it actually dangerous to talk into a camera while driving? So I'm going to spend 15 minutes in the simulator distracted, trying to give this monologue to that camera. And I'm also going to spend 15 minutes in here not distracted, just driving, and put my full attention on the road. And the team here are going to analyse my results and tell me how I've done. And given I was just doing 35 and a 25, probably not that great.
The National Advanced Driving Simulator was built to recreate the most realistic driving experience possible anywhere. It has a real vehicle cab in it. We can swap different vehicle cabs in and out. The motion base can travel 64 feet in the X and Y directions. And these are basically steel belts that are connected to large drives on either end. And then the hexapod portion of the simulator is hydraulic. That allows us to experience roll, pitch, and yaw. We also have a turntable that can turn 330 degrees in either direction. Overall, it has 13 independent degrees of freedom. We have absolute control over what time of day it is. We have control over the weather and traffic.
And yes, the graphics might not be up to modern video game standards, but after a few minutes in here with all the motion, your brain just accepts that you're driving.
Very broadly, we are interested in studying the relation between the driver and the vehicle to improve safety. So that encompasses things like driver impairment, driver drowsiness, distraction, or intoxication. So we bring drivers in, actually give them a large dose of alcohol, get them in the simulator, and we can see how they perform. We've also compared that to things like cannabis. So some of the first studies with cannabis and driving have been done in the simulator here as well. As Tom's driving in the simulator, talking to the video camera, I would expect to see him missing certain information in the driving scene. Generally, we find that interactions that take the driver's eyes off the road tend to be the worst. But even in situations where the driver's looking straight ahead, if their attention is pulled to another task, like talking to a video camera, that can also increase distraction and cause the driver to miss certain things. If the driver crashes, they essentially move through the vehicle or the pedestrian that they collided with, so we don't simulate the dynamics of a crash. But we are recording that the crash, we know the velocity of that crash, and we know how severe that crash would have been.
So how did I do?
About as well as we would have predicted. So let me pull up an example here. A vehicle is going to drive through an intersection. You actually have the red stop sign.
Yeah, I didn't see the stop sign, did I?
Completely missed it.
Whoa! Just did not see that. The thing is, I'm actually looking at the road there.
Yes.
But I'm not thinking about the road because I'm too busy thinking about what my next line is.
Exactly. We would call this inattentional blindness. So this is when your attention is off the road. Even though your eyes are there, you're missing information that's out in the environment.
Wow.
So we saw quite a bit of swerving at the beginning of your drive. You had some trouble controlling your speed. You were going about 35 through a 25 school zone. Yeah. Textbook case of distracted driving.
So I basically shouldn't film while driving.
Generally speaking, yes.
Thank you so much.
Sure, thank you.
Thank you so much to everyone at the National Advanced Driving Simulator at the University of Iowa. Pull down the description or click the link on screen for more about them. It is minus 38 degrees in here. I have never been anywhere this cold. I've had to insulate my camera so the batteries keep working and keep a microphone close to my body so the wiring doesn't freeze and fall apart. This is the United States National Ice Core Laboratory in Denver, Colorado, and I figured it was best to interview the scientists that work here outside this giant freezer.
We have about 20,000 meters worth of ice represented here, and that's from probably anywhere from 60 to 80 different boreholes around the world. The deepest one we have is about 3,600 meters through the ice sheet of Antarctica. In our lab, the oldest ice that we have is about 420,000 years old, and that's from the Vostok ice core drilled in East Antarctica back in the mid-90s.
When a new core comes in, we piece it up and ship it out to principal investigators. All of this is meteoric ice, which means ice that's fallen from the sky. They don't want any of the tundra or sea ice because it would contaminate the meteoric ice that we'd have. One of the principal investigators who was running an analysis can check his system from home, and he asked if somebody was eating potato chips in the break room because he started seeing a higher amount of sodium in his samples. And they said, well, yeah. That's how sensitive this is. If the mains fail, we have a natural gas fueled generator out in back. It automatically switches power to the freezer building. We're 100% backed up on everything.
Each one of these tubes contains a sample of ice from the Arctic or Antarctic, and the deeper underground the core was taken from, the older it is. All that fallen snow crushed down over perhaps hundreds of thousands of years, along with anything else that happened to be dragged along from the atmosphere.
Pretty much anything that's in the atmosphere, whether it's the atmospheric gases or dust or anything like that, eventually lands on the ice sheets of Antarctica and Greenland and will get buried and trapped within the snow. And as that compresses into ice, it preserves that information. So we can actually use these ice cores to recreate what our atmospheric chemistry was like dating back to about 850,000 years ago. We can also determine what global temperatures were and how they changed over time by studying the stable isotopes of oxygen within the water molecules. Essentially, they're looking at the ratio between O16 and O18. And by using a lot of modern day studies, they can figure out what the temperature was in the area where that snow fell. There's a wide variety of ways that we can date these ice cores. With Greenland cores, oftentimes we can actually see visible layers that change from summer to winter based on the dust concentration. So sort of like tree rings, count those seasons going backwards and get a date that way. And then occasionally we'll run across things like volcanic ash layers. And if there's enough material within an ash layer, we can use radiometric dating to get a very specific age on that volcanic layer. The margin of error in terms of our ages are usually within, plus or minus 10 years or so. So it's pretty accurate, especially when we're looking at ice that's a few 100,000 years old. By understanding the natural variations of climate change, we can better predict what's going to happen moving forward now that humanity has made a pretty significant impact on what's going on with our planet in terms of the amount of greenhouse gases that we put into the atmosphere over the last century. We can better understand the past, and using that knowledge of the past, we can better model what's going to happen moving forward into the future.
I'm at the Arecibo Observatory in Puerto Rico. It is one of the world's largest radio telescopes with a dish 300 meters across. I had seen pictures and video of this before I came here, but honestly, the sheer scale is impossible to get across on camera. It is massive. For 50 years, it's been listening to the sky, and one day, it might just save the world.
Arecibo has been part of discovering the large-scale structure of the universe. We've discovered prebiotic molecules in distant galaxies, the first millisecond pulsar, the first exoplanets. The big one, which everyone knows about, is the Nobel Prize for the discovery of the binary pulsar and the way that its orbit decayed exactly as predicted by general relativity. There's 50 years of discoveries here. I could talk for 50 years on discoveries of Arecibo.
One of the most incredible things about the observatory is this, the suspended platform that I'm standing on right now. This entire colossal structure is suspended in the air on cables, like a suspension bridge. There are no pillars underneath holding this up and getting in the way. All this weight is being carried by the 3 concrete towers around the dish. And this platform isn't static. Big parts of it move.
The telescope, by going a short way north and south, can actually see about a third of the total sky from here. The main bowl of this dish is spherical. The complication, though, is a spherical mirror doesn't have a point of focus like a hyperbolic mirror, which we're used to with big optical telescopes and most big radio telescopes. And so in order to get the signal to a focus, the Gregorian dome contains 2 smaller reflectors. These smaller reflectors actually bring everything to a point focus. And that means in the Gregorian dome we can have much wider band receivers and cover from 0.3 gigahertz up to 10 gigahertz in frequency.
Arecibo can do something that most radio telescopes can't. It can transmit. Famously, in 1974, it beamed the Arecibo message out to the stars, but there are also some more practical uses for sending big pulses of energy into space. Radar. Arecibo can bounce radar signals off planets, asteroids, and, well, anything nearby in the solar system. And it can build up clear pictures of what is out there in the dark.
The advantage of using the radar imaging is you can actually see the shape much better compared to the optical imaging. We can actually see even boulders on the surface if they are close enough, if it looks like a bone or if it looks like a sweet potato.
The S-band transmitter is a high-power transmitter that works at 2380 megahertz of frequency. That's the S-band. The whole transmitter is a megawatt of power. This transmitter produces a beam of power, and if you put your hand right through it, you can get burned.
We mostly observe near-Earth asteroids. When new asteroids are found, the orbit is not very well defined yet. The main thing that we can do is really enhance the orbit information. Transmit a signal, and when it hits a moving object, the wavelength of the signal changes depending on if the asteroid is moving towards the observer or away from the observer. And that way we can actually get an estimate to millimeters per second of the velocity of the asteroid. When new asteroids are found, the distance can be determined to hundreds of meters, even tens of meters. So we can get very accurate information of where the asteroid will be from now to a decade forward, or even a century forward. Asteroid Apophis, the preliminary orbit information showed that it actually might hit the Earth. After it was observed with radar, they could determine that it will go super close. It will probably disturb some of the satellites that are orbiting Earth, but it doesn't hit the Earth. And that's very important to know, because now we know that we don't have to send Bruce Willis to deflect the asteroid. Out of all natural catastrophes, impacts are the one thing that we can actually avoid. So earthquakes, volcanoes, they just happen. We can't actually help them. But if we can observe an asteroid early enough, we have opportunity to deflect it.
I'll be honest with you, this is not Mars, but it's one of the closest simulations we've got, the Mars Yard at NASA's Jet Propulsion Laboratory in Pasadena, California. This is where NASA tests out models of its rovers before they get sent to the Red Planet. And over there is where NASA's engineers can learn to drive one.
We have the Mars Yard, which is made of a few things. Some of them are rocks that we actually take to a lab to cook and ensure that they have the exact same compositions, and we bring it to the Mars Yard. Other rocks are actually not the same composition, but the color is the same, or the texture is the same. And the same thing with the sand. We bring sands from specific areas so that the color and the texture matches.
Out here in the Mars Yard, there's not just that simple model. Over in that hangar, well, it's not really a model of Curiosity, it's a full-size physical twin. It's not got quite all the electronics and there's no plutonium, but it's close enough to figure out what to do in tough situations.
All the instruments, all the mechanisms that we have, plus additional simulations, we put it all together and we integrate it right here with Maggie. 80 to 90% is probably the same thing we have on Mars. There's a few things that aren't. For example, the wheels themselves. The gravity is different on Mars, so you don't want to have the exact same thickness of material on the ones on Earth, otherwise you're going to break them very easily and it's not going to represent what actually happens on Mars. So the intent is try to dry run everything that we can with this one, try to simulate it, and then go for it on Mars.
Driving a rover comes with a strange problem, a time lag that, depending on where Earth and Mars are in their orbits, is anywhere between 4 minutes and 24 minutes. This is not a case of just grabbing a joystick and powering forwards. There is a lot of planning involved, because if you break that rover, there are no spare parts and no second chances.
I've been driving rovers since 2004, so 13 years now. I'm the person that has driven the most kilometers on Mars, only 16. We can go from really low-level commands, say apply 5 volts to a motor, up to a command of saying go there and avoid all the obstacles that are in between. The vehicle not only has a software on board to control the movement, but most importantly has software to determine if something bad is happening. Every day we use the cameras to take pictures. The images, they are stereo, so we can reconstruct the 3D terrain. From those pictures, we can determine what activities we can do at that location and where it is safe to drive. On Curiosity, we have about 20 people that are certified to drive the vehicle. We have different styles, different comfort levels in terms of risk or things that we are scared of. Some of us are particularly scared of sand, steep slopes. It depends on what problems you had when you were driving.
Every single day that we're going to spend with the rover on a specific site, it's very important for us to test as you fly. And what I mean with that is, as much as possible, do it here, because you don't want to be surprised when you try to Mars.
I have no idea what's going to happen next. Normally, when I do a video, I have a script and a plan, but this time, no such luck. This is the high voltage test lab at the University of Manchester, and the idea is that we're going to hit one of those with more than 1 million volts from one of these. I should probably get back down.
This is the UK's largest multi-purpose high voltage lab. We basically test, design and do research on all kinds of electrical assets. We also do use the lab for teaching. We have an impulse generator that can go up to 2 million volts. Historically, this lab would have been used to actually test how lightning affects an aircraft. But we've never tested a drone before, and a drone's actually made of composite materials, plastics. Is it going to fry the electricals? Is it going to fry the battery? Or is it going to be fine?
What do you think is going to happen?
I think it will blow up. I probably shouldn't say that, shouldn't I? But yeah.
This is the kind of capacitor that you might buy at a local electronics shop to put in a circuit. And this is the kind of capacitor that they use here at the lab. Each one of these red boxes can store 100,000 volts, and there are 20 of them in this tower. So when the trigger fires, all that power is going to go through the resistors in front of me, up, down through that little brown wire to the single point. Then it's going to go through the air as lightning to the ground rod. There's just going to be a drone in the way. Oh, here we go. Here we go.
Nice charging.
Yeah, here we go. Here we go. I think we got it. Oh, look at that.
Yeah, it's not even very hot.
That's actually a little bit disappointing. I was kind of hoping that
it
we'd
smells it. You smell that?
Does it?
Oh, yeah.
I probably shouldn't inhale that, actually.
Burn motor.
What I would do is, why don't we just take the battery?
Yeah, let's take the battery out. Battery's intact. Battery's still running. Let's try and switch it back on. I'm going to stand back just in case. Let go. No, the internals are dead. Battery's good.
The entry point is coming through the motors of the propeller, which is made out of metal, and it seems to have exited out of a point, which is almost the handles. Even though they are made out of plastic, there's still a sharp point, which means they have a high electric field. So you still will get an exit point, which is what's happened. But all that current has gone through the motors and all the electronics, which is pretty much fried.
But it seems to skip the battery.
The reason why the battery is protected, the battery does have a metal casing around it, if you kind of think about it.
So it's basically a Faraday cage.
It's a Faraday cage, so that has probably protected the battery.
Right.
But everything around it has been fried to bits.
All right.
What I would recommend is almost having something sticking out from the top.
Yeah.
Almost like a metal electrode again, so like a lightning interceptor. So that attaches to that point and you can have an exit point. We'll try and see if we can put a metal tape and a protruding part outside, which will hopefully attract the lightning so it doesn't go through anything else.
Let's do it. That's why we have a backup drone.
Million bucks.
All right. Here we go. The propellers! It's on its feet and the battery's still lit. Have we got communication?
Yeah, it's on.
All right.
Aircraft disconnected.
All right, let's bring it in. Okay, so it blew the propellers off. Man, they went.
They did.
Can't see any visible points.
On the last one, there was charring on the plastic.
So we've got the picture, similar to last time. Seems to be attaching to the propeller and coming out. There you go.
It's
so you
completely missed the lightning rod, hasn't it?
Yes. At the end of the day, this actually will tell you that lightning can be unpredictable at the same time.
Yeah.
And in all fairness, it did hit the propellers again and comes out at the same point.
Yeah, what are the streamers?
When you have a high voltage, streamers are what go up to answer the streamer that's coming from the cloud.
Right.
So when both of those connect, then do you get a channel.
Should we have a look at the sonar?
Absolutely. There you go.
There's the strike.
And
there's the streamer.
The streamer is still there.
Look at that.
The channel's already formed.
Yeah.
So the current's already going through.
Yeah, and you can see just little glowing embers. The motor's burned out. All right, so battery back in. No. No, it's dead. So the lesson is, if you're going to fly your drone in a lightning storm, don't. Thank you.
No problem, Tom.
Thanks, guys. If you want to test a scientific experiment in zero-G, you've got a few options. You could send it to the International Space Station, but that's expensive, and let's be honest, it's unlikely to happen unless you've got a few friends at a space agency. You could package it up into a small CubeSat and launch it, but that's still pretty expensive. You could take it along on a zero-G flight and strap yourself into a plane that's accelerating towards the ground at just the right speed to cause weightlessness. But that's still a lot of hassle, and a lot of expense, and a lot of fuel burned. But fortunately, there is another option. This is the drop tower at the University of Bremen in Germany. Inside is an enormous vacuum chamber, and for the last 90 minutes, powerful pumps have been removing all the air from inside, turning it into a near vacuum that's perfect for freefall experiments. And there's a drop capsule about ready to go.
In this experiment, I try to study the charge separation process through tribal charging, the effect that causes static electricity. During the microgravity, glass beads are released into a capacitor. In microgravity, you have enough time to trace your particles, and you can observe other interesting effects that aren't observable in normal gravity.
Acceleration due to gravity on Earth is roughly 10 meters per second per second. And without air resistance to slow things down, that drop capsule is going to start moving very quickly indeed. In the first second after release, the drop capsule goes 10 meters. Next second, 20. Next second, 30. Next second, 40. And then we've used up pretty much all the height there is. To get just one more second's worth of free fall, you would have to build this tower half as high again. Unless you do something really clever and start by going up.
The experiments are installed into a drop vehicle. That's the experiment itself. It's all the measurement and diagnostic tools. It's a computer controlling it. We throw it upwards with up to almost 30 G for 200 milliseconds and then into 0 G for almost 10 seconds then. And the deceleration finally by the end of the experiment has a value of about 35 to maximum 50 G. It should be very accurate because you can imagine if the energy is too large, then we would hit the ceiling. We would destroy our vacuum containment, which is the most delicate element we have in our house. We almost perfectly balance the center of gravity to the vertical axis of the capsule by adjusting some counterweights at appropriate locations in the capsule. The experiments are in fluid mechanics, it's in combustion, it's in fluid handling, it's in biotechnology, it's in physics and astrophysics, it's in fundamental physics, So almost any disciplines.
It's a little counterintuitive, but the capsule really is weightless, all the way up and all the way down. The forces acting on it remain the same, even as it changes direction relative to us. So, here we go. Launch time. The slingshot will fire, and in the 9 seconds that the capsule's in freefall, an 8-meter deep pit filled with polystyrene pellets will slide in over the catapult to catch the capsule. Hopefully. Thanks to everyone at the University of Bremen, at the Drop Tower, and to all the researchers who are testing here today. Pull down the description for more links about them and about their work. In 2003, the Human Genome Project finished a monumental scientific achievement, the first complete human genome map. A couple of decades later, and you can get a genetic test done by spitting in a tube and paying a couple of $100. But that's not quite what I'm here to talk about. This is Kubrick, one of the most advanced brain imaging centres in Europe. And here, they're not scanning genomes, they're scanning connectomes.
The connectome is a phrase that was coined several years ago, and it's to really encapsulate the idea of mapping all the connections in the brain in one go. Those connections are formed by what we call the white matter in the brain. So we know the brain has grey matter, it also has white matter, and these form these wires. We're also really interested in what we call the microstructure, being able to differentiate between the size and shapes of cells that may be only 1,000th of a millimetre across. What this scanner will enable us to do is to get information about differences across the whole brain in a way that would only previously be possible post-mortem.
Now, I'd be getting a scan myself, but alas, I have a bit too much metal in my body. Don't worry about me or the camera getting sucked into this, though. This is just the simulator that they train on. There's no actual magnets in there. The real scanner is over there.
This MRI scan of the magnetic field gradient allows you to be sensitive to the motion of water molecules over a distance of about 1,000th of a millimetre. To map somebody's complete connectome, first we have to acquire the raw data, then we have to fit it to mathematical models, then we have to reconstruct those pathways, and so we rapidly expand from a few hundreds of megabytes up to tens of gigabytes.
All the hopeful science fiction fans out there shouldn't get too excited. In the same way as copying someone's genome doesn't let you make an actual copy of them, just a baby that's an identical twin and that doesn't know anything, scanning a connectome doesn't mean that you can suddenly upload someone into a computer. Scanners like this generate roadmaps, not satellite photos. Heck of a roadmap, though.
I think we're a long way from being able to identify differences in personality at the present time, but that's not to say we won't be able to do it in the future. Generally, people are connected in the same way, but it's subtle differences in the shapes of the tracks that does seem to be highly reproducible. If we scan 300 people and then scan one of those people just one more time, you can easily identify them out of that 300 people. Essentially, any neurological or psychiatric disease that you can think of, they're all symptoms of malfunction of the brain. And we know that function of the brain relies on information transfer from one region to another. We can say things such as, there's something different with the integrity of the white matter. Potentially, if you can name a neurological or psychiatric disease, the information that we get from this scanner is going to be a boon and give us major new insights. And if we could bring the cost of the technology down, you could go in for your connectome scan and have the personalized treatment tailored to your specific connectomic deficit.
Right now, connectome scans are cumbersome and expensive, and they take a long time to process and visualize, but that was true of genome scans just 20 years ago. In a decade or two, connectome research might unlock just as many benefits for the world. This is a normal British terraced house. It was built around the turn of the 20th century out of bricks, mortar, and a lot of manual labour. Kitchen, living room, and a set of stairs in the middle that lead up to 2 bedrooms and a bathroom. And although the exact details might be different, about 1 in 5 houses in Britain look roughly like this, all built in a row. Trouble is, houses like this weren't built to save energy or to keep the heat in on a cold winter's day. Energy efficiency wasn't really a thing a century ago. And while there are all sorts of plans to modernise and retrofit houses, how do you know which plans will work? How do you do a controlled experiment when every house is different and the weather constantly changes? It'd be great if you could just, tell the sun what to do.
We're in the Salford Energy House, which is the only whole building in a climate control chamber. The idea really was to take a Victorian house and look at different ways that we could make it more energy efficient. When you test something on its own, like a boiler, you sit it in a lab and you test it and it will be X% efficient. When you actually put that in a whole house or a whole system, it then interacts with all sorts of other things like the fabric, the radiators, the controls. So understanding how things fit together as a whole house is really, really important.
This isn't some close approximation of an old terrace house made with modern techniques. This was a genuine end-of-terrace house from out in Manchester. It was taken apart and then rebuilt piece by piece here in an environmental test chamber at the University of Salford.
We had to get a bricklayer. The bricklayer was like 70 years old because actually the way that the bricks were laid in Victorian times, nobody does it like that anymore. He said he'd not laid bricks like that since he was a trainee. We've got, I would say hundreds of sensors. Every single appliance is monitored individually. What we can do here is also simulate human activity. We have actuators, so they're like robotic arms, which will replicate the open and closing of doors, fridges, windows. We can turn appliances on and off. Here we control the weather. We have a space next door with a big water tank, and there are layers of piping that run around that will push rain onto the side of the building, because rain never falls down, it always comes sideways. And then we also have a snow machine, and we also have wind machines, and we have a lighting system, so that's just radiant heating lamps connected to a theatre lighting control system, so the sun can pass around the building. All of those things can make a huge difference to the way a building performs. The first really big test we did, which was a whole house retrofit, we attached wall insulation, we improved the doors and the windows, and we improved the floor, and we reduced the heating energy by more than 60%.
There's always a trade-off with experiments like this. Yes, heating and cooling a large building that is inside another building is not massively energy efficient in itself, but compared to other industrial processes, it's not that bad. And if spending a little energy here saves a lot elsewhere, well, that's probably worth it. Thank you very much to everyone at the Energy House and the University of Salford School of Built Environment. You can see their YouTube channel here. I'll pull down the description for more about them and about the house.
Leica Blade menu tersembunyinya Mixul.
Well, it's been a minute. I've been working on a pretty complex topic, and in the meantime, I need to think of something quick. If only I had more time. That's it! How about a little taste of November in January? Do you have an electrical thing you want to have turn on at a specific time every day and then also turn off at a specific time every day? I know, so do I. But that sounds really hard. I mean, we all know how to make and break electrical connections with a switch. You just gotta touch the metal together and then pull it apart real fast. And we also have these clock things that have an hour hand that slowly turns in a circle twice a day. But you know, some of them only rotate once a day for those that prefer their time served that way. I wonder if we could connect the technology of clocks with switches. Oh look, it's a vat! Okay, like a door that's left its frame, that intro was unhinged. I'm sure you've seen these things before. They've been around for a long time. In fact, I'm not even sure how long they've been around. Thanks to that Nintendo thing all the youngins are playing with, internet searches involving the word switch are ruined. Now, I found a time switch from 1921 which automatically turns stairway lights off after 3 minutes. But that's not what I want to talk about here. I want to talk about ordinary timer switches, the kind where you tell it an on and off time and it repeats that daily. I suppose this is a sufficiently obvious idea that it got implemented in one way or another just as soon as we figured out the light bulb. All we really need is a clock that can actuate a switch. In theory, this could be as simple as a rotary switch which gets hit by the hand of an ordinary wind-up clock. When it collides with the switch, it would turn it from off to on and back. To make this a little more flexible, instead of giving that clock hands, we can use a wheel that rotates once per day. Then we could attach little actuators to that wheel that will hit the switch. And there you go! You just made a timer switch! Let's take a look at this consumer-grade timer switch. This intermatic time-all was a staple of American life, or at least some American lives, in the 1970s, probably? I'm having a heck of a time tracking down specific dates for this model's introduction, but it's old enough that it doesn't have a polarized plug, which makes it borderline useless today. But sure enough, it's basically a weird-looking 24-hour clock that has a wheel instead of hands, and hanging around the edges of that wheel are these little movable tabs marked on and off. You can move them by pushing them down, and then they'll slide around the edges of the wheel. Simply put the on time where you want it, then the off time where you want it. Of course, you also need the clock to be set to the right time. You set the time by turning the wheel so that the current time lands where the time of day pointer is pointing. Sticking out the side of the device near that spot is a little black knob that's also marked on and off. That is the actual switch mechanism that the clock activates. And when I turn the dial by hand, I encounter resistance once the tabs get near that knob. Keep turning and you'll see that the knob starts to move. And right when the tab hits the time of day indicator, the knob snaps into the off position. Cleverly, the on tab can only turn the switch from off to on. If the switch is already on, well, the on tab doesn't do anything as it passes the switch. Same goes for the off tab. If the switch is already off, that tab won't do anything. This not only prevents the timer from slipping into the inverse of what you want, but it also means that you can manually flip this to on or off to give a temporary override without screwing up the programming. The timer will resume normal timed operation when the correct tab hits the switch once more. I'll show you how that works in a moment, but I want to point out that since this really is just a clock attached to a switch, that clock could be powered by anything. It could be a wind-up mechanical clock, or a battery-operated clock, or even gravity-driven with chains if you were particularly eccentric. But as this thing's going to get plugged into a wall outlet, since that's its whole thing, the clock mechanism is driven by a synchronous motor. That's a special kind of motor that spins in lockstep with the frequency of incoming AC power. Since grid operators do a fine job of making sure that power runs at exactly the right frequency and will even make adjustments day by day to account for accidental drift, it serves as a reliable basis for keeping track of the time. At least, usually. Since the AC line voltage here runs at 60 Hz, that means the motor will spin at 3600 RPM, assuming it's a single pole motor. That's, of course, way too fast, so a ton of gear reduction is used to slow it down to 0.00069, nice, RPM, or 1 RPD, revolutions per day. Anyway, here's where the actual switching and the timing of that comes into play. First, let's talk about the electrical switch that makes this thing useful. In this timer, it's almost hilariously crude. Incoming power from the blades runs right to the terminals of the outgoing receptacle. And whoa, hang on. Those terminals? They've got bumps on them which actually engage with the holes in a plug. Finally, we found something. No surprise, it's old. Anyway, one blade has a simple wire link attaching it directly to incoming power, and the other runs through two formed pieces of brass that touch through a contact right here. The pokey-outy knob of the power switch attaches to a shaft running through the timer body, on the other end of which is a simple rectangular bit of plastic which either pushes the contacts apart or lets them touch. A simple 90-degree turn of that shaft is all that's needed to change switch states. As discussed previously on this channel, electrical switches should have a snap action to prevent arcing from damaging the contacts. Here, that's accomplished with a simple arrangement of two pieces of metal which act like leaf springs. They surround a square cross-section of the switch shaft, keeping a slight amount of pressure on it and holding it in place. As the shaft is turned, the corners of the square start to distend the leaf springs by an increasing amount, thus increasing the force required to turn the switch. But once the square is just past the 45-degree mark into a turn, the springs will now help turn the switch, and it quickly snaps into the next position. This design relies on the timer's plastic shell to hold the top half of the spring in place, as well as to put pressure right on this spot of the brass link to make the contacts actually touch. So then, here's how the automatic switching happens. There's more going on with those sliding tabs than you can see from above. As the dial turns with the passage of time, the on and off tabs slowly approach the switch knob. The off tab has a protrusion that will collide with this wing on the switch shaft. Time marches on though, so the tab will slowly rotate the switch. And once it's pushed far enough, the switch snaps into the next position, opening the switch contact. Notice that there are only two wings on the shaft. Now that it's in the off position, the off tab on the timer's wheel can no longer change the timer's state. The wings are parallel to the wheel, and at this point, are useless. Further into the timer, though, we find another pair of wings on the switch shaft, a pair in the opposite orientation as the first. The timer's on tab has a protrusion just like the off tab, but it's positioned inward so it can only collide with this second wing. Once it does, of course, it pushes the wing forward, turning the shaft, and eventually it clicks over into the on state. This staggered arrangement is how the manual override can work without screwing up the timer settings. The on tab can only ever turn the timer on, and the off tab can only ever turn the timer off. If it's already in the same state as the tab would turn it to, the tab has nothing to grab hold of. This design also allows you to pull the switch knob out slightly, which takes those tabs entirely out of alignment with the switch, thus turning this into a manually operated switch until you push the knob back in. A nice feature, I suppose. While this design works, and works well, it's also somewhat limited. You can only pick a single on and off time, and the shortest duration you can have between them is 2.5 hours. To alleviate these limitations, eventually Intermatic would change this design from sliding tabs to removable tabs. This timer here is one such example. The overall method of operation is remarkably similar to the first timer. We have a rotary switch, though now it's up here, and the on and off tabs simply push that switch into the next position when they collide with it. The green tab turns it on, and the red tab turns it off. The two tabs have their switch actuator pokey bits at different depths, so just as before, the on tab can only turn it on, and vice versa. The similarities don't stop there, though. Internally, we have a remarkably similar motor and gear reduction drive, and the switch itself is still quite crude. It's also damaged on this one because somebody decided they should hide a screw underneath the clock dial, and I didn't figure that out until after I went ham with a screwdriver and pliers. Anyway, this time they've refined the switch by making the switch blades double as the springs, which provide that nice snap action. But otherwise, it's still just as crude. Are these wires even soldered to the motor leads? Oh, but this time they did at least take care to switch the hot leg. In the old timer, if you installed it upright on the most common outlet orientation you'll find here, the switch broke the neutral. Very good. I mean, it wasn't polarized anyway, but still. Anyway, since you actually remove and replace these tabs on this design to set the on and off times, you can add more if you want a more complex program. When new, these timers came with 2 or maybe 3 pairs of tabs. But tabs are very easy to lose, and unfortunately Intermatic didn't think of designing some sort of tab holder into this to store them. You'd think this might be for that purpose, but nope, they don't fit there. So those extra tabs tended to disappear. Don't worry, they sell replacements. Actually, as a matter of fact, you can still buy this timer new, though stock appears to be dwindling. Also, you can indeed put the tabs right next to each other and the timer will work. So if you want something to be on for just a half hour, well, now you can do just that. Luckily, at some point somebody asked, why are we faffing with those tabs, and designed a timer like this one. Now, the face of the timer has 48 individual tabs along its perimeter, which can be up or down. Annoyingly, these things almost never bother with printing up is off, down is on, so it's always a game of trial and error setting one up. But once you figure it out, you've got all the flexibility this design could ever offer, and without the risk of losing the tabs, since they're now permanently attached to the timer. Internally, we still have a synchronous motor and gear reduction, making the dial rotate once per day by way of this drive gear. But now we have an off-the-shelf micro switch doing the switching with micro flare. A simple lever connects the switch's actuator to the perimeter of the dial. In this design, the dial acts as a very slowly turning cam, which that lever rides against. When the tabs are in the down position, they push on that lever, which depresses the switch actuator, allowing power to flow. However, when they're in the up position, they leave space for the lever to fall into, and that releases the switch, opening the contact. Microswitches have their own internal spring mechanism to make the switch action happen quickly. You can hear it clicking when I depress it manually. And since it always wants to push that actuator out, the switch will in effect turn itself off as soon as the lever falls into the cam thanks to a pulled up tab. This design also allows for a simple slider to provide a program override. Slide this over and now the switch is pressed in regardless of the tab situation. However, it won't automatically resume the program like the Intermatic timers will. It will only return to the program when you switch it back to timed operation. Now, in case you haven't realized, it's 2023. These days, we have more sophisticated ways of timing when things can and cannot get power. But mechanical timers like these still have their applications. I whip out a few during Christmas time for some indoor lighting displays. And it can be nice to set up, say, a floor lamp on a timer like this to give you some light when you get back from a day out and about. It may be basic, but it's still automation. And in the commercial realm, you still see similar timers used for things like defrost cycles in refrigeration equipment, lighting signage so it goes out after closing time, or even just exterior lighting in general. Though photocells are usually a better option since the sun does that thing where the days get longer and shorter. But as electronicals get cheaper and cheaper, well, now it's just as likely that when you need a basic timer, you'll be getting something like this. A microcontroller hooked up to a display, some buttons, and a relay makes for a very flexible timer. Want different programs for weekdays and weekends? Knock yourself out. Concerned about the time drifting with a power outage? Well, just stick a little rechargeable cell on the board and use a clock crystal as your time base. You can even get inexpensive timers which, after telling them where you are on the planet and the date, will automatically adjust sunrise and sunset times throughout the year, all without needing Wi-Fi or an app. And that's pretty neat. Still though, I can't help but admire the charm that is a clock which turns a switch. Or, I guess, presses a button in some cases. Take two basic things, smush them together, and you can make a pretty handy new third thing. Do it well enough, and you can even change the world. Thanks to Mike for sending these timers my way back when, and of course, thanks for watching. I've been working on a pretty complex topic. That's it! How about a taste of Little November? I mean, we all know how to make and break electrical connect. I suppose this is a sufficiently obvious idea that it got I could have made that work. I suppose this is a sufficiently obvious idea that it got implemented in one way or another just as soon as we figured out the light bulb. Why is the pacing so wrong? The knob snaps into the off position. Except I just turned it on. One blade has a simple wire link attaching it from the thing. Internally, we... Good God.
The Gotthard Base Tunnel is the longest and deepest rail tunnel in the world. 57 kilometers through the Alps, literally through. It's called a base tunnel because it's at the base of the mountain. At its deepest point, there are more than 2 kilometers of rock above. It's so far down into the ground that the earth in there is hot. Without ventilation, the air temperature would be more than 40 degrees. Around the turn of the century, there were 2 devastating fires in road tunnels under those mountains, and the authorities here in Switzerland want to make sure that nothing like that can ever happen again. How they do that is fascinating. So here's what's going to happen. We're going to see the control centre that watches over the tunnel, and also visit one of the intervention centres with the firefighters and first responders that'll step in if the worst were to happen. And then I want to show you what I reckon is the most important bit of safety equipment. It isn't anywhere near the tunnel, and most people will probably never notice it. But before that, we start at the control centre, just over there.
In the Gotthard Base Tunnel, there are 6 freight trains and 2 passenger trains per hour per direction. This means that at the same time there are several trains inside the tunnel in both of the two tubes. The gutter-based tunnel is divided into 3 thirds. If there is a disturbance in one of these thirds, the train can be diverted at one of the 2 changement points into the other tube to bypass the disturbed section. There are different sections to control the traffic. The signal box controls the track. The movement authority is given by the signal box and by the traffic controller. If there is a disturbance on one of the systems in the tunnel, then we have different possibilities. First of all, we get noticed by an alarm that there is a problem. They first of all try to fix the problem remotely. If this is not successful, they can send people on site to try to fix it.
This tunnel is actually a bit of a tourist attraction in itself. You can get driven in down a service tunnel on a guided tour and end up at this reinforced, windproof visitor's window with 8 centimetre thick glass and watch the trains go by at anything up to 230 kilometres an hour. That was terrifying.
If a train has a technical problem, first of all, the train driver tries to reboot the train system. If it's not successful, we have the firefighting train, which goes into the tunnel to tow out the broken train. In case of an incident in the tunnel, let's say a fire, we have 2 intervention centers, north and south. Intervention center means firefighting stations. They get an alarm, and within 5 minutes, usually both of the firefighting trains go into the tunnel from north and from south at the same time to fight the fire. They have the obligation to be on any point in the tunnel within 45 minutes. Firefighting train is a convoy of firefighting trucks on rail. They bring water in, foam liquid, they bring special equipment, tools to handle any possible situation inside the tunnel. At the 2 emergency stops, there is a possibility to refill the water. If people have to be evacuated in the tunnel, they do not walk out of the tunnel because it's much too far. The train brings them to one of 2 evacuation stations, where the passengers can go into the evacuation tube. This evacuation tube is under pressure, so fresh air is streaming in. They are safe because they have enough oxygen and smoke cannot enter. Then they go to the next evacuation section where the evacuation train is waiting for them. We have to be able to evacuate the entire tunnel within 90 minutes.
As I went round today, one of the team said that if there ever is an evacuation or a fire in the tunnel, several other things had to go wrong first. Yes, you can never protect against every possible weird circumstance, but you can try. Which brings me here to what's basically the middle of nowhere in Switzerland, about 15 kilometres away from the south entrance to the tunnel, and to this gantry over the tracks. 15 kilometres sounds like a lot, but at the speed Swiss trains can travel, that could be about 4 or 5 minutes. And while it doesn't look like much, this gantry scans every train at speed before it even gets near the tunnel. There are sensors on the track around here too, and if the train has anything unbalanced, any hot spots that look out of place, anything poking out, then it's not going into the tunnel.
We have laser systems which measure the profile of a train. Maybe the load of a train has moved and doesn't respect anymore the necessary profile to enter a tunnel. We have heat detection, where we can detect overheated axes or overheated brakes. All these controls, they happen at usual commercial speed of the trains on different points all over Switzerland. And we get about 200 alarms per day from these measuring stations. If we do not confirm an alarm, within 30 seconds the train is stopped automatically. It's not an emergency stop, but it's quite, you feel it. If a train seems to be wrong, it gets to a side track where it has to wait. If the inspection says this train is okay, then it can continue its journey. If not, the owner of the train has to resolve the problem before the train can continue its journey.
Yes, there are lots of systems in place for if the worst happens, but prevention is better than cure. And for me, this gantry is the most important bit of safety equipment here, because the best solution is to stop problems before they even start. To make it easy to synchronize the audio and video later. Except that's not really an answer to the question, is it? If the question was, why do YouTubers clap at the start of their recordings, then yes, that's the answer. It's to help with synchronization. A lot of the time, audio and video are being recorded separately. The microphone on my collar is sending its signal to a small and very beaten up recorder that's clipped to my back pocket. The camera is recording its own sound too, and saving that as part of the video file on its memory card, but it sounds terrible. So when I'm working on the edit and putting the two files back together, it's really useful to have a short, loud impulse sound at the start of both files so I can synchronize them just by looking for the spike on the display. There's a couple of extra complications there though. First of all, should that synchronization be perfect? That camera's about 2 meters away from me. The speed of sound changes a little with temperature, but roughly that's about 6 or 7 milliseconds. Not enough to care about here, but once you start putting the camera further away, 10 or 20 meters for long shots, that sound can take a couple of frames to reach the camera and the audience. That would feel weird, so I'd have to slip the audio a little. That's why it's worth double checking the synchronization by looking for the frame of video where the hands touch. Plus, some cameras, particularly old GoPros, actually add some sound delay to the video file. The synchronization is terrible. So if I've got 3 or 10 or 100 different cameras all looking at the same thing, I can use that clap to synchronize them all. Get it close by looking for the spike, confirm it by looking at the hands. Actually, worst case, the audio can actually be late by up to maybe 3 frames or so, and the chances are no one will mind or even notice. Actually, the sound on this video has been 3 frames late ever since I cut back this shot of me. If you did actually notice, well done, I'll put it back to normal now. I suspect that works because brains are used to correcting for small speed of sound lags for people shouting from a distance, but that's just speculation. I can't actually find any research to back that up. And because the viewer might have things like a cheap external soundbar and a television that adds more lag, it's best to synchronize as close as you can. If the production's got a high budget, they might use a clapperboard instead. That means the editor has a record of which file is which take of which scene at the start, and they can sync up the audio at the same time. But all that is still not an answer to the question. It's the answer everyone gives, but it's not what the title of this video is actually asking. This isn't why do YouTubers clap at the start of recordings, it's why do YouTubers clap at the start of videos. I've done that plenty of times before. I did it in this video. Why do we leave a bit of technical junk in there? Why do I set up a really nice shot and then ruin it by showing the setup part, letting my camera fuzz about with the autofocus and make the whole video worse? Well, I can't speak for everyone, but my reason is it sets the audience's expectations and it makes it feel more authentic. When I'm filming on my own with a static camera, it can sometimes look like I'm just stood against a green screen. But clapping, walking into frame, letting the focus settle, showing that behind-the-scenes moment, it proves I'm here. It makes me seem more trustworthy. For someone vlogging from the bedroom, keeping those claps and the preparation in, letting the audience see a little bit of the slip-ups and how it's made, it helps make a connection, helps make them relatable. I don't need to be relatable, I don't really want to be relatable, but trustworthy. Trustworthy is good, and leaving the clap and the walk in the video establish that I am one person with one camera, that I don't have a crew on this shoot, and that I am actually here, wherever here is. Sometimes I'll leave that in when I actually do have a crew. It's all about the aesthetics. Showing that setup, leaving that synchronization clap in, it's about fitting the message to the medium, planning not just what you want to say, but the subtext of how you say it, and handling all the subtle cues that connect performer to audience and say, it's okay, you can trust me. You know, in the first Jurassic Park movie, there was that scene with the glass of water in the car's cup holder with ripples on it to show just how heavy the approaching T-Rex's footsteps were? Well, this thing behind me is technically called the Large Mobile Shaker, but the folks here at the University of Texas, they call it the T-Rex because it's a machine designed to shake the ground itself.
We have 5 shakers. They go from a small one that's right behind me, and we call that an urban shaker because you can bring it downtown and not get into trouble with shaking. And then we have very, very large ones, Liquidator and T-Rex. Liquidator is a low frequency vertical shaker where we generate surface waves, like surface waves from earthquakes, but ours are linear typically, and earthquakes can be nonlinear. T-Rex is a triaxial shaker. Triaxial means that the shaker only one at a time. It can shake vertically, it can shake horizontally, and it can go transverse. It can go up to about 60,000 pounds force vertically and about half horizontally.
The T-Rex is on a fairly low setting right now, but don't worry, we're going to be turning it up shortly. It doesn't feel like much here right now, but we'll get there. And you might think this would just be used for destructive tests or validating computer models. No, this is useful for research and exploration.
We have been all over the United States. We have sensors that we've designed, and we will push in because they're pushing rams on the back of Liquidator and T-Rex so that we can install sensors and then watch the wave go down. Many times we're watching the wave propagate away from us, but other times it's very helpful to watch the wave going down and seeing how poorly the soil might behave due to large amplitude shaking, which is what you don't want.
We've now switched to horizontal shaking, and this is about half of what the T-Rex can do. I've only ever been in an earthquake once in my life. It was very slight, but it felt like this, the ground underneath my feet, the thing for me to rely on. Right now, it just isn't stable anymore.
We just came back from Wyoming, where they're going to build new power plants, and the earthquake design is critical. And we generated a 6,000 foot long wave. Now we generated a 2 foot long wave too, but going through the range. So that means we could evaluate the stiffness profile down to a half a mile with no boreholes. That is really a true accomplishment and a very, very cost-effective addition to the design of the plant. So this is a sensor. It's a big magnet with a coil. The coil's going through the magnetic field. We were out there in Wyoming and the darn cows walked by. Fortunately, they didn't break any cables, but we had to stop testing because they made more noise. They were right out there and we were a half a mile away.
And this is the highest setting that the team are allowed to use here on campus, as we just show off the features do. 27 tons of force being pushed into the ground, only 10 times a second. It turns out, doesn't show up on a 30-second camera, and the world is shaking.
Oh my goodness, every time we go someplace, we'll make sure the level won't damage structures. Once we were on the UCLA campus and maybe didn't watch what we were doing so much, and people came running out of the building, and that got us in trouble.
Almost all the letters that get sent in the United States are processed automatically. You put a letter in a postbox, it's taken to the closest processing center where cameras and computers take a picture of the front of the envelope, read the address with optical character recognition, OCR, and it's then passed on to the right truck or plane. That deals with pretty much everything, even the handwritten letters. But what if your handwriting is really bad, like really bad, or the envelope got a bit damp and the ink blurred and ran? The Postal Service sends the picture of the envelope here to the Remote Encoding Center, the REC, in Salt Lake City, Utah. And it's the job of the folks here to turn scrawl and blurred ink into actual addresses. It's a quiet day here today. Mail volumes are low in the middle of summer, so while it's not busy inside, I'm going to see if I'd be any good at this.
We're in the last remote encoding center in the United States. Back in 1997, when we had 55 RECs open, all of those RECs combined keyed 19 billion images. The OCR technology is so good that in 2021, as the last REC remaining, we only keyed 1.2 billion images. Right now we have about 810 employees here. Shortly we're going to be teaching Tom how to process some of this mail. It'll be a lot of fun.
It's important to say that I can't show you any actual mail, not the envelopes, not anything. If any appears in the background on a screen, it'll be blurred out. That's all considered strictly private. And besides, I'm not going to flash random people's addresses on the screen of a YouTube video, particularly when they'll usually be written in distinctive handwriting. You can probably work out how that could go wrong. But there is a stack of demonstration mail, envelopes and addresses used for training, and that's what I'm going to be tested on.
If you drop off a piece of mail, it makes it to the local processing plant. If the machine can't read your handwriting, one of the keyers here will type in the missing information, and the information goes right back to the plant, stays within automation, which is a whole lot cheaper than having somebody physically sort that piece by hand.
All right, okay. What do I need to do?
You'll be putting your last name and first initial into that.
Yeah. I looked at the keyboard to look for the numbers and realised that this is a...
That is not a standard keyboard.
That is not a standard keyboard. Other than the QWERTY letters and the numpad, everything is different. Okay.
To make everything faster for us, they did some weird things with the keyboards that they've provided us. The home row, A, S, D, F, those also work as your numbers. You can't reach up to the top of the keyboard to hit 1, 2, 3.
How to key the outward portion of a mailpiece image.
We're calling outward the city and the state.
City and the state, okay.
Siemens came up with this in the 90s. So they decided C coding is going to mean zip code. Outward is going to mean city and state.
Okay.
Inward is going to mean the street address.
And that's now the language that you use because that's what they decided.
To make it faster to key these letters, our keying is a small extract of what's on the letter, and then it compares it to the known good addresses in the database. Every known good address in America is sitting on our servers in the back. If it's good, the piece just goes away and you're done. If it matches a couple of good addresses, then you'll get a list and you'll choose out of that list which is the address you were trying for. It makes it a whole lot faster than typing out the entire thing.
Key in the first 3 characters of the first word in the city name. Okay, first character of the second word, 2 character state or territory abbreviation.
It's the 3+1 rule. It's the same for the street addresses.
Okay, press the go key when ready. Go. So that is LETMS.
Oh, the 3+1 rule. If there's not 3 characters, you got to do a space.
Ah, okay.
I got to clear it out with the enter key.
So that is LE space TMS.
CS key.
CS. Oh, city state. Got it. Okay.
Some pieces are buffered and some pieces are live. That live mail will be sitting on a conveyor belt going around the machine. Those flats and those packages, if we don't key them in 90 seconds and get the information back to that machine, it dumps it off into a reject bin and somebody has to hand sort that. So for the letters, they run them through the machine one time, they store them off to the side. A few hours later, they put them in the machine the second time, anticipating that we've processed everything that was missing.
Oh! I'm guessing that's like Dixon Hill or something like that. I can't tell if that's DIC or DX. Ox Hill.
And I see it as
Ox Hill.
Yes. Okay.
Okay. Oh!
Remember, these are the easiest ones to read on the test.
Yeah,
so
I realized that.
Get ready. Every year we have fewer and fewer pieces. We've got fewer people handwriting mail, and we have OCR technology that's really good. I'll bet we went from somewhere in the neighborhood of less than half of the mail being read by a computer in the 90s to nearly 99% of letters being read today. The OCRs that are reading the letter mail, I think it's close to 99%.
Yeah.
So we get the 1% of the junk, and we improve about half of that 1%.
Right.
The job here may be getting harder because pieces are harder to read. Because if the computer is so good and can't read it, it's a lot more likely it's not a good piece of mail to begin with. The address was destroyed somehow, or the customer had bad information for the address.
So they've put Fort Lauderdale as an abbreviation, so I would put FT no matter what, not FO.
Correct.
I don't autocorrect that.
Do it how the customer did it.
Okay.
We're not sleuths, we're not picking out details. You key by the rules, you type in the address information from what you can clearly see. Now the street address works similarly where you'll do all the numbers, and then 3+1.
Ignore the direction word and key the street name. If the direction word is the only word, key it. Okay. 3+1 rule, so go. All right. Ah, but I looked down to find where the numbers are. 720. Where's... No, yeah, that's West Boulevard, so you include that and you hit street.
Yes.
400 Little Way Street.
We have internet service from 3 different providers. We have 3 fiber optic lines coming into the building at different points, so if any one point gets chopped off, we can maintain service because we're the only REC connected to every plant in the country. Over 300 processing plants, including Guam and Anchorage, Alaska, and Juneau, Alaska, and San Juan, Puerto Rico. It's asking for numeric and it's in C coding, so it wants the zip code.
It wants a zip code, 35804. Go.
So if both the machine can't read it and a keyer isn't able to decipher it here, the machine at the plant sends it to the reject bin, and then somebody will manually handle it. And then if they can't figure it out, it would either get returned to the sender, and if there's no return to sender information, then it will go to the mail recovery center.
Okay, final test. Here we go. Numeric. We don't have a numeric, so we hit none.
Correct.
Then it's outward, which is MOK space HICS 2545 HEAD Street.
Nice.
Okay. I mean, what speed would I have to go here?
7,150 keystrokes per hour.
It's the speed with which you have to read that, parse it. It's much tougher than I thought it was going to be to keep everything in your head. And this is easy handwriting, like nothing here has been blurred.
Yeah, and you haven't even gotten to the ones that are upside down or backwards or have four, or packages that have 4 sides to them.
Right, and it would be an average of 4 seconds for each one to keep up the pace.
On average, it's about 4 seconds that somebody's got one of these on their screen.
Wow.
And you did an incredible job for just learning these rules right now. I'm impressed.
All right, thank you. I'll take that. That's thank you so much. Normally when I'm filming somewhere like this, I try and set the camera so it's got that kind of professional depth of field. You know the shot. Everything in the background is blurred, but there's a windmill back there and I really want that in focus. I had to throw out nearly all my script for this video. Normally when I go and film somewhere, I try and write everything in advance. I research things in detail before I get there. When I arrive somewhere, there should be no surprises. But I knew, even as I set up for filming on the roof of Royal Flora Holland, that perhaps this video wasn't going to go to plan. Good morning, it's just after sunrise here in Aalsmeer in the Netherlands. This is one of the largest commercial buildings in the world, and today, just like every weekday, millions of fresh flowers are being bought and sold inside. Sort of. This market has existed in some form for 100 years, and recently there have been some changes. Because here's how the story's supposed to go. The auction room will be full of buyers, frantically pushing buttons to bid as cart after cart after cart after cart after cart of fresh flowers are paraded in front of them in a massive, perfectly timed logistics operation. But I'm not sure that happens anymore. All the English language sources I found are out of date because things are changing at the Dutch flower market. It turns out a lot of the Dutch language sources are out of date too. The truth is that a famous, decades-old tradition has ended, in the same way that video rental stores gave way to streaming. A thing that tourists came to see and that a lot of people think still happens is no more. So I'm going to update the English-speaking world. The famous Dutch flower auction clock is no more. But the flower market that it was once part of is still there, and it runs on an almost incomprehensible scale.
Dit gebouw is ongeveer 800 bij 500 meter en we maken altijd een vergelijking met Vaticaanstad. Vaticaanstad past op het vloeroppervlak van onze veiling. En als je het hele gebied hieromheen, waar ook de kopers zijn gevestigd, dan zijn we ongeveer zo groot als Monaco. Onze coöperatie is ontstaan uit een fusie van een heleboel andere veilingen. En daarmee zijn we de grootste van de wereld met een omzet van 5,6 miljard euro het afgelopen jaar. We zijn een coöperatie van kwekers. Wij proberen een optimale prijs voor hun producten te realiseren tegen zo laag mogelijke kosten. Dat is allemaal gestandaardiseerd, zodat het allemaal zo efficiënt mogelijk kan gebeuren. En daar zijn we heel succesvol in.
Efficiency. We'll come back to that shortly. I often complain that the camera doesn't capture the scale of something that I visit, but in this case it's not just the camera, it's that there are no good sight lines anywhere in that warehouse. It's next to the airport, so I can't get drone shots, and it's not that tall, so there's no one point where you can overlook the whole thing. Look, it's so big that the employees sometimes use bikes inside to get from one side to the other. It's a giant, high-speed, hyper-optimized clearinghouse. Growers deliver flowers in the early morning, and by lunchtime they're sold and on their way to buyers, either via the warehouses next door or in trucks that ship them onwards.
Royal Flora Holland heeft ongeveer 40% van de wereldwijde export in bloemen en planten. Dat betekent niet dat we een marktaandeel hebben van 40% van de totale wereldmarkt, want landen produceren ook voor hun eigen markt, local for local. Maar alles wat geëxporteerd wordt, ja, daar hebben we dus 40% van.
So, okay, it's a logistics warehouse. The scale is impressive, but it's nothing too special. The famous part is how the flowers are sold there. If you've heard of a Dutch auction, this is one of those auctions, I think the biggest one anywhere. There's lots of historical footage of the big auction clock. It used to be analog and then went digital. Hundreds of flower buyers all sat in theatre seating as racks of flowers are paraded in front of them. For each lot of flowers, the clock counts from a high price to a low price. First to press their button stops the clock and pays whatever it's showing. Press too late, someone else gets the flowers. Press too early and you've paid too much. It's an amazing system. It looks great on camera. It's been covered by loads of media over the years, and it's gone. I thought the pandemic would have caused some changes, but no, it turns out this all changed years ago. The internet enabled remote buying, so the theatre seating got emptier and emptier over the years. There's now a reputation system for the sellers, so buyers could know that the quality was as advertised without actually inspecting the flowers in person. By the mid-2010s, those racks of flowers weren't being pushed through the auction rooms, and by the end of the decade, the rooms were closed down. I got shown one of them. It looked abandoned and actually a little bit sad. The replacement is many auctioneers running many clocks over the internet all at the same time, sitting in cubicles with microphones.
Op de veilingklok staat heel veel informatie over het product. De kwaliteit van het product, de duurzaamheidscertificaten, of het A1 kwaliteit is of A2 kwaliteit is. We hebben 2500 kopers, maar die zitten natuurlijk niet allemaal op één klok, want we hebben in totaal 35 verschillende veilingklokken. De technici hebben het zo kunnen oplossen dat je geen voordeel ervan hebt of je nou hier om de hoek zit of dat je zeg maar koopt vanuit Londen.
The flower auction isn't like some old railway that gets kept alive as a tourist attraction or preserved by a group of volunteers running what's basically a reenactment society. It turns over billions of euros every year, and if tradition gets in the way of that, then tradition has to go. And I think the sources aren't up to date because this famous thing has slowly been replaced isn't a nice, friendly story. And besides that, 60% of what goes through that warehouse is sold in advance by contract now, bypassing the clocks entirely. Some of the really large buyers, like international supermarket chains, are making private arrangements with sellers who don't use the warehouse at all, because those chains are big enough that they can handle the logistics themselves, and that saves them money. The tourists do still visit. The scale there is still impressive, and I think it's still worth going to see if you've got some spare time near Amsterdam. But if you are hoping to watch the famous Dutch auction clock, well, these days it's a lesson to anyone who thinks that they won't need to change with the times. In the business world, tradition is rarely more important than money. And speaking of money, today's video is sponsored by NordVPN. Seriously, it actually is. I'm a little bit surprised too. I'm on the road a lot at the moment, and it turns out that having a magic button that tells websites and phone apps that I'm in my home country is really useful. Without a VPN, lots of sites that I'm visiting keep putting everything in Dutch and giving me prices in euros. Sometimes there's not even an option to change that. Even YouTube is sometimes like, oh, ik zal je nooit opgeven. Last week, I was blocked from accessing a UK government site until I turned on the VPN. And also, when I'm researching, sometimes I find American sites that completely block me because I'm in Europe and they can't be bothered to comply with European privacy laws.
The tests are done with the outer wheels at loads corresponding to heavy vehicles, but we can also install on each arm single wheels, dual wheels, or also 2 axles or 3 axles. When the machine runs, we can also move the wheels laterally to reproduce the effect of real traffic. And you can also change the loads. On a single axle, we can go from 4.5 tons to about 8.5 tons. So sometimes we can overload the pavement to accelerate deterioration.
It takes a few minutes to creep up to speed, and it's kind of a little bit unnerving standing here because it started off, it's very slow, this is all very safe, and now there's a lot of metal coming towards me, faster and faster.
This machine can run at about 100 kilometers per hour. The usual testing speed is 70 kilometers per hour because we don't want to go to the maximum, but we can go to 100 kilometers per hour.
I thought this was up to speed. I think it's still getting faster. I've got dust in my eye from the wind.
We instrument usually the soil and also the pavement layers. So in the soil we put generally our displacement transducers or vertical strain transducers to measure the vertical displacements. And then in the bituminous layers, the most common instrumentation is strain gauges. We use also temperature sensors because temperature variation is very important for the pavement response. And we use also accelerometers or geophones to measure the vertical acceleration and then to get the vertical displacement.
Testing on this carousel doesn't mean just a few hours or a few days. A test here can last months. The carousel constantly rotating, with the wheels travelling at anything up to 100 kilometers an hour with a 1,000 horsepower engine powering them, so that years worth of pavement stress and road damage can be built within weeks. There are actually 3 different circular test tracks here, and the carousel can be taken apart and moved between them. That way, while a test is happening over here for a few weeks, another track can be torn up and rebuilt for the next set of experiments. And the tracks can be divided into sections to run several different tests at once. One of the tracks is also watertight for testing how pavements behave on wet or soaked ground. And I really hope that the size and scale of this thing is coming across on camera, because I've had to change my microphone to the windproof one because of how much turbulent air this thing generates. Those Those arms are twice my height. They are massive. It is genuinely unnerving to be standing here, not able to see this, with just this noise behind me.
There are some limitations, of course, because it's an accelerated test. We cannot control the climate conditions. And then there is aging of the bituminous materials. They become more brittle, and obviously we cannot simulate that because we have to do the test in several months. We include one reference section with the material that we know. We can make a comparison with the classical material and correct the results by some coefficients to adapt to real conditions.
It's tempting to think that in the 21st century we can test everything by computer modelling and simulation, but those simulations have to be grounded in truth somewhere. You can't build those models without real-world data, and when you're dealing with public safety and billion-euro infrastructure projects, sometimes there is no substitute for just building something real. It's early morning at an aerodrome in southern France. For some of the videos I make on this channel, I need to do huge amounts of research for. I need to make sure the script is right, fact check every single word. And sometimes it's more about the experience, because there is a man called Christian who flies microlight aircraft alongside some birds. Allons-y!
Alors au départ, je n'étais pas pilote de quoi que ce soit. J'ai toujours été passionné par les oiseaux, mais il y a une trentaine d'années, j'ai lu un article sur la disparition d'une espèce dans la nature, l'oie naine à front blanc. Je me suis dit, si moi j'arrive à guider de nouvelles générations d'oies naines à front blanc, sur un nouvel itinéraire, je vais pouvoir commencer à les réintroduire dans la nature, parce qu'elles avaient été exterminées par les abus de la chasse, là où elles passaient l'hiver autour de la mer Noire et la mer Caspienne. Elles se reproduisaient en Scandinavie et passaient l'hiver autour de la mer Noire. Et nous l'avons fait en 1999 avec ma femme, avec 33 oies naines qui nous ont suivis sur un long trajet depuis le nord de la Suède jusque sur un site d'hivernage au bord du Rhin en Allemagne, où les oiseaux ont mémorisé avec nous ce nouveau trajet. Et dès le printemps suivant, après un hivernage en Allemagne, ils sont retournés seuls sur la réserve qu'ils avaient quittée, donc ça avait bien fonctionné. Comment est-ce qu'on arrive à voler avec des oiseaux, avec un ULM? Il faut pouvoir élever les jeunes oiseaux, mettre les œufs en incubateur, avoir des couples qui se reproduisent ici, et élever les jeunes comme le feraient leurs parents. C'est le phénomène d'imprégnation, to imprint. Parce que depuis la naissance, au sortir de l'œuf, nous sommes en présence avec les oiseaux. Dès ce moment-là, ils nous considèrent comme le parent. Donc tous les ans, j'élève des oiseaux comme si j'étais leurs parents et ils me suivent naturellement en vol comme si j'étais leurs parents. On passe beaucoup de temps dans la nature avec eux, on dort avec eux. Je me baigne ici dans cette mare avec ces petites oies quand elles sont toutes jeunes et il faut les habituer au son de ma voix. Les oiseaux reconnaissent très très bien les traits du visage. Il faut les habituer au bruit du moteur très tôt et à la silhouette de l'ULM. J'ai obtenu des certificats pour pouvoir élever ces oiseaux, c'est des espèces protégées. N'importe qui ne peut pas les élever. Et pour pouvoir également voler avec elles, il faut des certificats particuliers. Je vole presque tous les jours avec les oiseaux, quand le temps le permet évidemment. Il ne faut pas que le vent soit trop fort, il ne faut pas qu'il pleuve de trop, quoi. Ces oiseaux ont besoin de voler pour rester musclés, parce que si je les abandonne pendant quelques semaines, faut tout recommencer après, parce qu'il faut les remuscler. Quand on a des animaux de compagnie, on promène son chien le matin, le soir, pour qu'il dépense de l'énergie. Et chez les oiseaux, c'est pareil. Donc ils ont du plaisir à voler avec moi, mais comme j'ai tellement d'expérience, j'ai des milliers d'heures de vol avec les oiseaux, il n'y a jamais d'accident. Je pourrais éventuellement perdre des oiseaux si je ne savais pas observer mes oiseaux, pouvoir savoir quand un oiseau est fatigué, et du fait qu'elles sont grégaires, ces espèces, il y a toute une gamme de vocalises qu'elles expriment, et j'ai appris à reconnaître tous ces sons, ce qui me permet d'anticiper aussi ce qui va se passer en vol. Je dirais, pour simplifier les choses, que c'est pas moi qui enseigne à ces oiseaux à voler avec moi. Ce sont ces oiseaux, depuis 27 ans que je vole avec eux, qui m'ont enseigné comment bien voler avec eux. Mais ces oiseaux me suivent en vol, c'est pas moi qui les suis. Mais sous le vent, je les laisse devant la machine pour pouvoir mieux les contrôler, je les observe, mais ils épousent tous les mouvements de la machine, ils se placent devant ou derrière ou sur le côté, mais c'est la machine qu'ils suivent et la personne qui pilote la machine. Si on est deux ULM à voler ensemble, l'autre pilote a élevé aussi ces oiseaux, ils le connaissent très très bien, et selon la technique de pilotage, on peut s'échanger les oiseaux en vol. Les vols pour la conservation des espèces, ça ne concerne pour le moment qu'une espèce, l'oie naine à front blanc. Et parallèlement à cela, je propose des vols avec les touristes pour pouvoir collecter de l'argent pour financer mes différents projets. C'est des vols qui durent que 35 à 40 minutes, mais lors d'une migration, c'est vraiment un long voyage qu'on fait sur des milliers de kilomètres. Je vole 4 heures en général, c'est très éprouvant parce que je vole avec beaucoup d'oiseaux, des groupes qui font une trentaine d'oiseaux. Il faut être très très concentré. Le vol avec un passager, c'est plus un vol de loisirs, où on a beaucoup de plaisir en vol, et nous avons des gens du monde entier qui viennent voler avec nos oiseaux. Dans la même matinée, j'ai parfois 5 ou 6 nationalités différentes. Il y a parfois des personnes handicapées qui ont du mal à se mouvoir dans leur corps et qui volent comme les oiseaux avec les oiseaux. Et puis il n'y a jamais deux vols semblables. Les oiseaux sont différents selon l'aérologie, selon le tempérament du passager. C'est un devoir pour moi de communiquer auprès du public la nécessité de devoir protéger ces oiseaux. Depuis que je vole, je n'ai toujours volé qu'avec des oiseaux. Si je n'ai pas d'oiseaux en vol, je m'ennuie.
Wow! Christian, thank you so much. Merci beaucoup.
You're welcome.
Incroyable. If you buy a clock here at the Radio Transmission Station in Anthorn, the National Physical Laboratory, NPL, broadcasts a time signal out to the UK in a simple enough format that the cheap electronics inside this clock can understand it and run accurately for over a year on a single AA battery. And at NPL's base in London, I asked their team how it all works.
What we have in Anthorn are some very high-end cesium atomic clocks, like the ones we have down here. We broadcast from there, we monitor the signals at NPL, and accordingly put out steers to those clocks to correct for any change. Because it's a very low frequency, it's 60 kilohertz, it has very low susceptibility to atmospheric effects. We steer from NPL based on measuring what Anthorn is broadcasting at the level of nanoseconds. That is a nanosecond, the distance light travels in 1 nanosecond, 30 centimeters. All that is taken into account.
So that seems simple enough. The official timescale is kept in London. I wasn't allowed anywhere near the official atomic clocks. I don't even know if they're actually at NPL's headquarters or not. They might be somewhere else. They told me nothing. But up north here, this transmitter has separate atomic clocks about 400 kilometers away from the base, or 1.4 light milliseconds away, because there's a light speed delay, a latency of about a thousandth of a second between the transmitter here and the base in London. Because the team at NPL know exactly what that delay should be, they can issue corrections if these clocks start to drift, even by nanoseconds, billionths of seconds. Officially, the accuracy is much lower than that, of course, partly because they keep a very wide safety margin, and partly because I can introduce a 1 nanosecond drift to this clock by doing that.
What is really important when you're transferring time is not about the latency, but understanding the latency so you can take that out of the equation. From the NPL, we disseminate to the UK over radio broadcasts. Essentially, that offers the entire UK mainland several milliseconds of traceability to UTC. We also have the fiber-delivered service for a regulatory compliance in the finance sector, guaranteed at the microsecond.
And that's fine, I can understand all that, but then that leads to another question. How does NPL know if their clocks in London start to drift? Sure, they've got many of them, they cross-check, and a second in the 21st century is defined by the number of vibrations of a cesium atom, but still, they can't be perfect. They're meant to show the international standard UTC, Coordinated Universal Time. So what if NPL's official source of timekeeping truth drifts from that standard?
UTC, or Coordinated Universal Time, as the name suggests, is coordinated globally, contributing data from multiple atomic clocks to generate what is the global timescale, UTC. What we have here at NPL is the UK's timescale, UTC NPL. We have a whole suite of atomic clocks, cesium clocks, hydrogen masers, and our cesium fountain, the Bureau of Weights and Measures, based in France, take the data from the clocks around the globe and inform each of the national labs how offset it is from UTC.
And that's where the buck stops, in Paris. Unless you start getting into physics and relativity and light cones, and that's way beyond me. Why does it matter? Well, first of all, finance and high-frequency trading, but also science. Things like the Square Kilometre Array, a planet-wide array of radio telescopes that's being planned and built right now. When they're listening for incredibly faint radio waves from space, all the telescopes around the globe have to be synchronised with that level of precision, or the whole experiment could fall apart. So then I had a final question. When accurate timecode is being sent from so many places, when the public can get time that's more than accurate enough for almost every purpose, from navigation satellites in space, why is this signal still important? And the team from NPL had a rather serious answer.
Time really is an invisible utility. It underpins our digital infrastructure, whether it's the synchronization of the energy grid or the telecom networks or finance. We are so dependent on GPS and other constellations. One of the problems we face is those signals are easily disrupted. It's the equivalent of a light bulb on the moon. One of the things we're doing at NPL is to ensure that the UK is resilient for the future.
This Sunday, the South Terminal at London's Gatwick Airport will reopen to the public after nearly 2 years closed. And I figured that reopening would just be a case of the team here turning the lights back on, dusting off some equipment and getting back to business. But from talking to the folks who are getting everything ready, it turns out that mothballing an entire airport terminal for 18 months and then reopening it again is much more difficult than you might think.
In March 2020, when the pandemic struck, we obviously realised there was going to be a significant downturn in traffic. So we took the decision to close one of our terminals. Gatwick Airport would generally see upwards of 900 movements off of our runway on a busy summer day. During the height of the pandemic, we were down to 2 or 3 flights a day, with certainly less than 500 passengers on certain days. I think it's fair to say in March 2020 we all thought it'd be over in 2 weeks' time.
If the terminal had been shut down for just a week or maybe a month, then yes, things would probably have just kept ticking over. But there's some point at which upkeep is required. In the same way that you're not meant to leave a car sitting unused for more than a couple of weeks, the mechanical parts in things like the baggage belts and jet bridges need to be run, tested and maintained regularly, or they might not start up ever again. Closing the terminal does reduce costs, yes, but it doesn't make them zero.
There's a number of core services we've had to keep running. We had to do regular maintenance and safety checks on all of our passenger boarding bridges and airfield equipment, water systems, lighting systems, power, fire, life safety systems, everything that's there to look after the people and keep everyone safe. But things like, heating and lighting in various areas and power for escalators and lifts, they were all shut down, mainly to save money during the crisis. We had to make cuts wherever possible. We've been taking the opportunity to use the space for filming. Film companies have been coming in and doing various shows around the airport, some of which I think will be airing in the next few weeks. A large number of our workforce have been furloughed, and since the 1st of October we've had everyone back in to get the airport back up and running. Now as passenger numbers start to grow, we are actively recruiting and we need to increase our workforce by a significant number. We're reopening 85% of it straight away. We've got a phased plan for our airlines moving back over from North Terminal over 3 days, but all the infrastructure will come online more or less from day one. In terms of a challenge, it's the biggest one I've done at Gatwick Airport. It's been open for 60 odd years, that's now been closed for the best part of 2 years. Buildings don't react too well to that sort of thing. The scale of what we're doing here is we've often likened it to opening a smaller airport completely from scratch. It is a huge task that we're undertaking. I'm feeling really confident actually. I think we're in a really good place to do it.
The first flight from the South Terminal is scheduled to leave on Sunday in the early hours of the morning, so it'll probably be about 3 a.m. when the first passengers go through the doors, and they probably won't know or care that the terminal's only just opened again. They'll just want to get to their destination. If everything goes to plan, they probably won't even know that the terminal was ever closed. A few weeks ago I was looking through records in the British National Archives for a separate video idea that didn't end up going anywhere, but while I was researching I found a completely different report, secret and restricted when it was written, but now unclassified, and it was the first time in a long while that I've read some old archive file and my jaw has literally dropped. It was called Possible Sites for Completely Contained Nuclear Explosions in North Yorkshire. North Yorkshire is a beautiful area that includes 2 national parks. This is the middle of one of them. It is stunning, it is historic, it is not somewhere that I expect anyone to try and set off a nuclear explosion. The report was written in June 1969, so just for context, we're talking full space race, white heat of technology era. Neil Armstrong would set foot on the moon only about a month after that report was written, and the report is talking about peaceful nuclear explosions, which was an idea that was in fashion among some nuclear scientists and policymakers at the time. Maybe, the theory went, we could create artificial harbours and canals using nuclear bombs. No more years of mechanical digging, just put a few well-placed nukes in the ground and boom, 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 there's your new canal. Or maybe we could help stimulate production in gas wells, basically nuclear fracking. Or, and this was charitably the most practical idea, create enormous underground cavities for gas storage instead of having to use big above-ground tanks. The US did run a couple of dozen nuclear tests like that under the rather biblical title Operation Plowshare. The Soviet Union eventually ran more than 200. But those are stories that have already been told by a lot of other people. By the 1970s, the US and the Soviets would work out that it was a bad idea. If you use a nuke either for fracking or to create underground gas storage, the radiation ends up contaminating the gas. But until that was figured out, well, I don't think many people have actually noticed the records about it since it was declassified, but it turns out that at least some people in the UK were interested as well. Those people worked at the Gas Council and the Atomic Weapons Research Establishment, and the report shows that they were seriously trying to work out if nuclear bomb gas storage caverns were a good idea. I kept researching and found they commissioned a full study laying out the pros and cons, comparing the cost to other methods of storage. They had picked a site, which was here. Actually, literally, exactly there, bottom of that ravine, Wheeldale, in the middle of the North Yorkshire Moors National Park. The plan was, buy all the land for about a mile around, drill down 2,000 feet, about 600 metres with a special extra wide drill bit, big enough so they could drop a 25 kiloton nuclear bomb down to the bottom of the hole. I say drop, lower. It's a big enough bomb to annihilate a city in the open air. Plug up the hole, cover the top so nothing comes out, hopefully, evacuate the 1,000 or so people who live nearby, just in case, and then, not much would happen on the surface. It'd be a bit of a jolt and a rumble, a few birds startled into the air. The local towns of Pickering and Whitby, about 10 miles away each, they'd feel a minor earthquake, and maybe a couple of buildings would get a few small cracks in them. I'm not kidding, that's what the report actually says, it just phrases it a little bit more delicately than that. It's not clear whether the locals would actually have been told what was going on, but I think it would have been impossible to hide. After that, they would let the giant cavern that had been created 600 metres down, cool for a few months, and then flush out and remove most of the radioactive stuff that was left behind, which it turns out would have been a lot more difficult than they thought at the time. Finally, they'd put some pumping equipment in here at the top, and presto, giant underground high-pressure gas storage tank for relatively not much money. And after a couple of years, they can sell most of this land back. Cost of the explosion in today's money, adjusted for inflation, about £9 million, which is not actually bad for a giant gas storage tank. I suspect that was a very optimistic estimate, though. Even that was a bit more expensive than setting up liquid natural gas storage above ground, but once you've made the cavern, it's much cheaper to run this way. If that is the explosion explosion works as predicted, and if there's really no radiation left over, there were a lot of risks. Now, as far as I can tell, this never got anywhere near the Prime Minister's desk. There was never some high-up government meeting trying to work out whether they should nuke a bit of a national park. I suspect it would have been a very bad political decision, and a very bad environmental decision, and a very bad financial decision. And look, I'm sure there is some possible alternate history where this happened, but things would need to have been very different. The last reference I could find is from November 1969. The plan was worked out in theory, and the minutes of the meeting from then say that further thought would be given to what action should follow. And at some point in some other record that I missed, or maybe that is still restricted, I'm sure there'll be a note that says they decided not to pursue the idea. Peaceful nuclear explosions would eventually be banned by treaty, conveniently just after the point at which the US and Russia found out they weren't a great idea, and the North Yorkshire moors, thankfully, were never nuked. I'm not saying this is definitely a plot for a British Ocean's 11 style heist caper, but if there are any screenwriters out there watching this, I feel like this one might be for you. British coins have the year they were manufactured right on them, so if you're a coin collector and your dream is the full set, it's not just a case of finding one of each design, you also want each value from each year. But in 1933, Britain didn't need any more pennies. There were plenty in circulation, so the Royal Mint, who make or mint coins, decided they wouldn't make any 1p coins that year. That's not unusual, it had happened before. The trouble is, King George V needed some. It was tradition for the king to bury a full set of new coins from that year in the foundations of new and important buildings as they were constructed, and you couldn't use old coins for that. So the Royal Mint did make some 1933 pennies. No one actually kept the records of how many there were, but it was probably 7. Which means that while the face value of those 7 coins is a penny, they're so rare that the price at auction these days is easily more than £100,000. And over at London Coin Dealership, I got to see one of them.
This is from a private collection, one that's been loaned to us very kindly. It's great because it's such an iconic coin, we get lots of visitors coming to see it. Usually these coins disappear into safes and are never seen again. The last sold in 2016 for a hammer price of around £140,000. It's the first time one's been sold for many, many years, and one would imagine if it was to come on the market again, it would sell for even higher.
So there are probably 7 1933 pennies. 3 are in private collections, I got to film one of those, 2 are in museums, and the others, well, that's the possible heist movie. Because remember, the king buried some of the coins. One of them was buried under this church in Middleton, West Yorkshire. I say was because in 1970 it was stolen. Whereabouts still unknown, although presumably if someone in Yorkshire finds a 1933 penny in their grandparents' coin collection, there's going to be a bit of suspicion. And after this theft, the local bishop ordered that the coins under this church should be dug up and sold in order to prevent them falling into the hands of thieves. That's one of the pennies that's in private hands legally now, which means there is 1 building and 1 buried coin left. The last 1933 penny is buried somewhere under the foundations of Senate House at the University of London, or at least everyone thinks it is. No one's checked since 1933. You'd have to dig it up. And I doubt that anyone actually knows exactly where it's buried, unless they've done a huge amount of research and found some original blueprints, which, to be clear, I haven't. And besides, according to the university, the whole package is buried very deep, not exactly where you'd expect, which does sound like what someone would write if they're trying to discourage amateur treasure hunting thieves. But Senate House is right here in the middle of London. There is some construction around here today. A few people in high-vis jackets with power tools. And while it's not exactly cracking the vault of a Las Vegas casino, well, I don't have a plan for you. And I don't recommend anyone try it for real. But it is a heist movie waiting to happen. Seriously, don't try it. This isn't the movies. It's just a coin. I don't have any plans. How do I make this sound not sarcastic? The alternating current running through these power lines changes direction constantly, a full cycle, back and forth, 50 times a second. 60 in some other parts of the world, but here in Europe, 50 times a second. But that transmission isn't perfectly efficient. There are imperfections and stray electromagnetic fields, and a little bit of that power becomes vibration, which makes sound at that frequency of 50 hertz, or 100, or other multiples of 50. That's the mains hum that you can sometimes hear coming from power lines, or maybe from speakers that aren't quite plugged in properly. Also, that hum isn't exactly 50 cycles a second. The grid frequency shifts slightly and constantly over time as the engineers in charge balance supply and demand. It's only a tiny fraction of a shift, but it's there. The whole grid runs at the same, slightly wobbling, almost 50 hertz, no matter where you are. That mains hum can be really annoying for people recording audio. You can hear it in the background sometimes. But if you were to log what that wobbling grid frequency was every second of every day, keep all that in a database, and then compare it to recordings with mains hum on them, then in theory, you'd have a perfect watermark to prove the time when anything was recorded. I talked to one of the forensic experts who works with it and also set them a challenge.
Historically, what's had to happen is we've had to record the grid frequency data ourselves by literally plugging a recording device into the mains. The National Grid have recently released their data, 7 years, recorded right at the source. It's fairly simple, actually, signal processing. You're looking to see if there is a component around 50 hertz or one of the harmonics. I would hesitate against advising anyone to present themselves to a court as a forensic expert, but this type of evidence has been used in court to date recordings. The longer recording you have, the better. As an absolute minimum, I think about a minute. If it's a noisy recording, or if the ENF isn't particularly clear, then the longer recording you have, the better.
So, find the mains hum frequency in the footage and then write code to match it against the millions of possibilities in the National Grid logs. Does it work? Well, to find out, I asked some friends of mine who make videos to send me over some of their raw footage, straight out of the camera, unprocessed, unfiltered, and I asked the forensic team, can you timestamp it? First up, footage from Taha.
There's quite a strong component here, and you can see it's got a bit of a wobble. We use a signal processing algorithm to extract the peak, and we constrain that algorithm so that it can't suddenly jump up here. So even if there is a higher amplitude something up here, it will stick to this curve. Then compare. If we know that a recording was taken on a certain day, then we just need to give it a day's worth of national grid data. If we're not sure when it was taken, we'll throw everything at it and it'll take a bit longer to process, but it's not prohibitive.
Spot on. Got it to the second. Although it's important to say that the team never said they were certain about the timing, only that they had a very high chance of being correct. And yes, they were. Next up, footage from Hannah Witten, sex and relationships educator. There
wasn't a component at around 50 Hz. So here we have the axis 49 Hz to 51 Hz, and we can see no apparent ENF trace. So I'm now going to change the axes up to around 100, and then we'll be able to see the harmonic component around 100 Hz. Because it's quite strong and seems to be behaving in a way that we'd expect the ENF to behave, we can be fairly confident that this is an ENF harmonic. What's interesting about this one is it sort of appears halfway through the recording. Maybe there's a little bit of something earlier on. But so there's a possibility that maybe Hannah was moving around when she made this recording, getting closer or further away from mains powered equipment.
Maybe the mains hum was coming from something on a timer or a thermostat in the background that just switched off, but the timestamp was accurate. So the next test was Steve Mould from his Science channel, and I thought that this one would be easy because he sent B-roll. He's not talking, it's just ambient noise, and also he is holding a fan that's plugged into the mains.
There's no strong component at all for ENF, so the next step would be to look at the other frequency regions to see if we can identify any harmonics. How loud the person is often doesn't have much of an effect. It's often environmental noise that would be lower to mask ENF. There is possibly something here, but because we haven't got a strong trace, it's sort of fading in and out, we wouldn't be confident to use this for an ENF analysis.
Sometimes it just doesn't work. As a last test, I sent over some of my old footage from when I was filming against green screen in my tiny flat last year. I was sneaky though, and I hid an edit in there.
What could happen with an edit is you'll have a sudden jump in the ENF frequency. In that case, it's quite likely to be an edit. It's possible that the ENF trace will just sort of stop. The reason for that could be because it's got an edit in, which in this case we believe it has. But it could also be because you walked away from the source of the ENF energy.
Like any forensic analysis, this isn't some magic tool that always works. Compression can stop it working. You need minutes of uninterrupted audio to have enough confidence in the result, and sometimes there might be no background mains hum at all. But I love this because it's an accident of technology that's created a tool that would sound like science fiction 20 years ago. It's this stamp, $8.3 million for about 40 milligrams.
The stamp's called the British Guiana 1 cent magenta. It's the absolute pinnacle of rarity in stamp collecting. It's not a variant, it's not a watermark variety, it's not a printing error, it's a straight normal postage stamp of which only one survived, and that's what makes it unique. So this was actually produced at the local printer office, so it was only ever intended to tide the colony over for a week or two. This 1 cent stamp also, it's believed, only paid a newspaper rate, which meant that they were used just to post newspapers locally, and newspapers even back then were immediately disposable.
There may be more expensive stuff by weight. Antimatter is often called the most expensive stuff in the world, but I don't think that should count here for several reasons. First, there's no way for anyone, no matter how wealthy they are, to buy a gram of antimatter in the shops or at auction. Second, substances aren't objects. The English language has a distinction between count nouns and mass nouns. It's a difference between there was a dog on the road and there was dog on the road. There's probably a less gruesome way of explaining that, but I guarantee that's going to stay in more people's heads. And the third reason? This stamp is non-fungible. Even if there was an antimatter shop just down the road, okay, let's go for something more realistic but also very expensive. Let's say there's a shop selling printer ink just down the road. 1 gram of printer ink is the same as any other gram. They're fungible. If you switch them out, it doesn't matter. This stamp is non-fungible, not just because it's the only one left, but because of its history. It's a unique object.
The stamp was actually first discovered in 1873 by a 12-year-old schoolboy. Now at the time it would have been nothing unusual because over time multiple stamps of everything else were discovered, but this is the only stamp in British Commonwealth history where no other examples have ever turned up. It passed through an increasingly prestigious list of the greatest names in philatelic history. Stanley Gibbons is the world's oldest stamp dealership. We have an auction house, 2 retail teams and a coin company called Baldwin's. Stanley Gibbons was lucky enough to purchase the stamp at auction in New York, and now it's on display every Monday, Wednesday and Friday just for conservation and light reasons, but indefinitely here in an oxygen-free conservation case.
This stamp has repeatedly set the record for most expensive, and every time it does, it adds another line to its already very long history. It's expensive because it's rare. Yes, there is only one of these in the world, and the way our society works, someone's got to own it. But outside stamp collector circles, not many people would care about the rarest stamp. But to the wider world, it's famous because it's expensive, and more fame will likely make it more expensive. And I guess I'm helping that cycle continue by making this video about it. I wouldn't claim to know the company's motivations, but I suspect that it's on display to the public here, at least in part, because the company is selling shares in it, and more fame will help it keep or raise its value. This is not an endorsement, by the way. I approached them about filming, they've not paid me, I have no desire to buy or sell a share in a stamp. But if you want to challenge this for the most expensive object in the world by weight and take the very, very tiny crown, well, the first step would be finding something even lighter than 40 milligrams, but just as historic and just as non-fungible. Good luck. Every time Boston Dynamics puts out one of the big YouTube productions, the world is amazed. The robots dance or they do parkour, all of which is very impressive, but it's under controlled conditions in a lab. It's not exactly a practical real-world use. So what are those robots actually being used for in the real world? Inside this mountainside in Western Austria is a hydroelectric power plant. I would have filmed this piece of camera actually down in the turbine hall, but it's a bit loud in here! At full capacity, 150 tons of water a second goes down from the uphill reservoir through the turbines in the cavern, generating 350 megawatts of power. And it's all run remotely. Switching this plant on and off is done at a control centre about half an hour's drive that way, where they also control 20 other hydro plants. On a normal day, no one works here at all, but for safety, someone does have to regularly drive out to all those 20 power plants and check that the physical things are all as they should be. So you can probably see where this is going.
We are using a robot to continuously do inspection tasks and therefore testing if this is plausible in the middle of the Alps. Energy robotics is putting software on robots to make them smart. We are a software company and we're not building the hardware. We are writing code. Therefore, we ask other companies to build the hardware for us or use existing robots already. We work with a lot of robot companies to picking the best robot for the task.
Boston Dynamics and other companies build the actual physical robots and provide a remote controller that someone can use to directly move the bots around. But they also provide an interface for computer code. The robot has built-in navigation and obstacle avoidance. So in the same way that you can write code to automate things on a regular computer, you can write code for the robot dog's computer too. Your code can learn the whole site that you're working at and tell the bot, okay, find your way to this point, look at this thing, take a picture and a temperature reading, and if that picture doesn't look like it should, or there's something blocking your way, let us know about it.
The robot is not remote controlled, it's doing that task autonomously. That means we teach in a certain mission and then the robot does the repetition of the mission. But it also be in the future able to do something called click and inspect. That means we have a digital twin of the environment and then we're just saying what the robot needs to inspect and the robot plans the path towards the inspection point and get the information. The robot autonomously extracts that information and reacts based on the results. Means either it sends an alarm if it's out of the norm or it just collects the information and then put it into the report at the end of the mission.
You can send robot dogs into toxic or radioactive environments that humans shouldn't be in, but this isn't a particularly dangerous site. They let me in, after all. It's just inconvenient to drive here, particularly in winter, when snowstorms might close the mountain road entirely. This is a place designed for humans, though, which is why robots with wheels or tracks aren't an option.
So it's important to have a robot which is capable to operate in human environment, because all the infrastructure humans have built have been built for humans. So therefore, we need a robot to be capable of interacting with this environment, meaning simply if we have a situation like here, where we need to climb stairs, we're using a robot on legs. In the substation, where we have flat ground, for example, we're using robots on wheels or on tracks. We're developing a skill which we'll use in oil and gas, where many of our robots are actually working, which we call man-down detector. So that if the robot detecting someone lying on the ground because of whatever incident, then the robot sounds an alarm and therefore bring in the troops to help the person lying on the ground.
This trial will succeed or fail based on two questions. First, does it work reliably? And second, if so, is it cheaper overall than sending out people, particularly when there might be a shortage of engineers soon?
The goal is to support human inspection and on the long run to replace certain parts, especially those where humans need to be sent in hazardous environments. In Germany we have about 8,000 substations. All of those need to have inspection and the number of substations is growing due to the change to renewable energy. We need to have more robots on the ground because we have not enough engineers in the workforce right now and we need about 400,000 more in the next 10 years. The robot can perform up to 12 hours of inspection, so 60 minutes walking around, 60 minutes charging, so a lot of inspection every day. So the next few years we're also testing assisted manipulation, where the robot is with a human doing manipulation tasks within infrastructure environments. In the future there might be fully autonomous manipulation, but that is probably some years to go.
If this works, and if it gets rolled out, then the power companies will be saving employee time and therefore money. In the same way that 20 power plants can now be controlled from one centre, 20 power plants could be inspected from one centre, with actual human engineers dispatched only when there's actually something wrong that needs to be fixed. And I suspect it will be a while before the robots start to take over that job as well. Yep, I am standing somewhere windswept and talking about infrastructure. I have a style. Also, that whooshing sound you can hear? That's the other turbine that you can't see in this camera shot. Anyway, power grids. They have to balance supply and demand. I've talked about that a few times in the past here, but as a quick catch-up, if there's not enough power being generated, things break. But if there's too much power being generated, things also break, and arguably in a worse way. There isn't a battery in the world big enough to deal with daily peaks and troughs of national demand, so power grid engineers have to make sure that the power being generated is always close to the power that's being used. There are a lot of possible technologies to help with that balance, and I've talked about some of those before here too. Pumped storage that uses a lake as a giant battery, or even the big lithium-ion setup in Australia that's only caught on fire once so far. But all of those technologies assume that supply and demand will balance each other out over time, usually over a few hours. What happens if you always have too much power? Welcome to the Orkney Islands in the far northeast of Scotland. About 22,000 people live here on around 1,000 windswept square kilometres, and they have so much renewable energy from wind and waves and tides that it's genuinely a problem. Solution number one is turn off the turbines.
2013 we were producing up to 130% of our electrical needs. So there can be quite a lot of curtailment on several turbines. There's active network management. The wind turbine will be shut down because the network can't handle the load. There's been a moratorium on any new grid connections. There is potential for some micro generation, but nothing of any scale. So when you're in a place like Orkney, where you have some of the best generation potential, it's a complete waste.
Turning off the turbines isn't a good solution, it's wasteful. Depending on the time of day and year, these islands need between 7 and 46 megawatts. It's almost always windy here, so a couple of big commercial wind farms like this can produce all the power the folks here need. But they've also got 500 domestic turbines, privately owned. 1 in 12 households generate their own power, because why wouldn't you? Once you've paid the installation costs, you'll probably turn a profit year after year after year. One of the things I struggled with writing this script is that there is so much going on up here. There's an electric hybrid plane being tested at the airport. There are tidal power experiments, wave power experiments. Every type of renewable energy, almost, is being tested here. There's not much solar. And as a backup, for the very rare days when the wind is calm, there are interconnector cables that can pull up to 40 megawatts from the Scottish mainland. But okay, they're generating a massive surplus of power, and they're connected to the British national grid. So surely solution number 2 is use those interconnectors. They can just sell the extra power back to the mainland. Well, those 40 megawatts that the interconnectors can handle, that's not actually all that much.
The interconnector cables we've got are small. We reckon there's 2,000 megawatts of tidal and wave generation around here. We reckon there's 17,000 megawatts of offshore wind within a couple of hundred kilometres of here. The interconnector was built for an old day when you used to burn coal and send us electricity. That's gone. We don't do that anymore. We now need to be in a position where we've got a better way to get the power from these islands away.
If the new interconnector is built, it'll carry enough power for all the turbines Orkney could reasonably put up in the next few years. They could power most of the Highlands of Scotland. But building that new interconnector will cost £250 million. National government requires that the islands approve plans for enough new turbines to make sure it's going to be used before it's approved. That's all still in the balance politically. So solution number 3 is that the islands could start using more electricity. There's already a larger share of electric cars here than anywhere else in Scotland, but most vehicles still use petrol or diesel. That could change. There's still a lot of oil heating. The ferries, vital for getting around, still burn fossil fuels. The transition is a slow process. No one's going to scrap a perfectly good car or heater or ferry unless they have to. But there are plans. And Orkney's also had a hydrogen fuel system for years to help soak up a bit of the excess power.
We're producing hydrogen from effectively spare electricity. That's why we started. Taking electricity, putting it into fresh water, and it splits the water into hydrogen and oxygen. We're getting rid of the oxygen and we're just capturing the hydrogen. We're compressing it and then we're using it in this fuel cell. We have ferries that operate within the island. One of those ferries is able to be powered by this fuel cell when it ties up alongside at night, and it saves it running its own engines, or it saves it drawing power from the grid. This is just the start of something. This equipment is experimental, and believe it, it's not efficient. This is not the best way of doing it, but we're finding our way into new territory. We try and unearth some of the challenges so that when we scale this equipment up, then those faults have been polished out.
These islands are years ahead of the rest of the world. This is the test bed. This is a small version of the changes that the whole planet is going to make. The transition to renewables is happening faster here in Orkney than, I think, anywhere else in the world. But as you travel around the islands, it just seems normal. Nothing's visibly changed. But the lessons that they're learning here will hopefully pave the way for the rest of the world. Red telephone boxes like this one are an icon of Britain. Or, well, they were. Nowadays, the boxes that are left are falling into disrepair and ruin because there's not much demand for payphones these days. If a little village wants to save theirs, then the phone company will sell it to them for £1, enough to make the contract legal and binding, but they won't keep the phone connected. So, what do you do with a disused phone box? Well, one of the options being installed right here might help to save lives.
Community Heartbeat Trust is currently the leading organisation for the provision of community defibrillators in the UK. To date, we've probably positioned 6,500 community defibrillators or thereabouts. It costs somewhere between around £1,600 and £2,200, depending on the equipment.
It turns out the logistics aren't quite as simple as buy a defibrillator and stick it in a box. A defibrillator is a medical device. If it's poorly maintained or it breaks, then it could be worse than useless. It could actually do harm.
So it's no use just putting it in and then forgetting about it. These need to be looked after, and it's got to be as good in several years' time as it is on day one. And it's got to be sustainable. It's not just about raising funds initially, it's also about ongoing costs and ongoing fundraising to make sure that this is actually looked after for the entire life that it's going to be in the community. Well, the first thing we need to find out from the process is, is the kiosk actually available? They can't decommission it unless there's a mobile phone signal for emergencies. When a community contacts us, we'll let the local ambulance service know that a defibrillator is going in, and then it's available in an emergency. When somebody phones 999, the ambulance service will be able to say, there is a defibrillator, it's located at the phone box on the corner of X and Y roads, and if the cabinet is locked, they'll give an access code. Once the defibrillator is used, you just take out the old pads, put on new ones, run a self-check to make sure the defibrillator is working properly, and then it's ready for action again.
And there's another question. Who pays for the power? The box is connected to the national grid, so the light and the phone could work back when it was an actual phone box, but it doesn't have an electricity meter. It's never needed one.
The electricity is there to provide electricity for the cabinet because there's a heater in the cabinet. It's not for the defibrillator. The defibrillators all work off batteries, and the heater in the cabinet obviously keeps the defibrillator above freezing in cold weather. That's really quite important because batteries do degrade in cold weather. The electrodes are water gel, so they will freeze. British Telecom, who's a major phone company in the UK, are the people who actually originally own these. It actually costs BT money to take out the electricity, so they would rather leave the electricity in. What they do with us is they donate that to us as a charity, and then we provide the electricity to the community. So the estimated cost for a kiosk to run it for a year is about £5 to £10.
All of this might sound good in theory, but the question is, could a bystander with no medical training actually use one of these to save a life? To answer that, I've come to the headquarters of the East of England Ambulance Service, who are going to let me try their training defibrillator. It doesn't actually produce a shock, we're just going to use it on a dummy, but it is as realistic a simulation as it's possible to get. So here's the story. Someone has collapsed, someone else is doing CPR, and I've been sent by the emergency operator to get this.
So the very first thing you do is turn it on and listen to the voice prompts. It will tell you to follow it calmly, which is a really important thing to do.
So we assume that there's someone here doing CPR, and now I have to take this off.
Call emergency medical services now.
Okay, we've done that.
Adult mode.
Yes.
Follow the voice prompt calmly.
Okay.
Remove all clothing from chest and stomach.
It's really important that all of the clothing is removed. We want a bare chest. There are concerns over maintaining dignity. Life comes before dignity.
Take out the pads from the bottom of the device, okay.
The next thing it will ask you is to apply the pads to the chest. So the first pad you're going to put on the patient's right shoulder, and the second pad you're going to put just below their left armpit.
Just
peel off the pads labelled 2 and stick to the bare skin of the patient, exactly as shown in the picture.
Shown in the picture, just below there, okay.
Do not touch the patient. Analysing heart rhythm.
At this point it will tell you not to touch the patient, and that's really important. It's going to be analysing that heart rhythm. One of the ones it's going to be looking for is where the heart is just wobbling around, where there's no regularity to it and it's not able to pump blood. What it needs to do then is stop that heart with an electric shock. Once it's stopped it, the natural pacemaker of the heart can kick back in and put the heart back into a normal rhythm where it can pump blood.
Shock advised.
Okay.
Stand clear. Press the flashing orange button now. Shock delivered. Begin CPR now.
If they are in a rhythm that the AED can shock, it will increase their chance of survival about 10% per minute.
Reanalysing heart rhythm in 1 minute.
So I've arrived at a call where there is a defib, it has been used and it's been used successfully, and the patient has started breathing again prior to my arrival.
Analysing heart rhythm.
It is the human equivalent of turning someone off then on again.
Shock advised.
If you haven't had any form of training, you can still use a defibrillator. You shouldn't be prevented from doing it, but you should be trained in order to get the most efficient usage of that equipment.
So I assume this would continue until emergency services actually arrive?
So yes, once we arrive, we'll take over what you're doing, we'll attach our defibrillator and take over management of the patient.
I realised when it said start CPR that I don't actually know about that, I only know what I've picked up from media, so I'm hoping I was vaguely in the right position there.
Yep, absolutely.
I need to go do proper first aid training. Thank you. I mean, that was lovely. Like the steady glow as it went through, and then boom, boom, boom from each one.
Yep.
I like how the wads of newspaper just shot up after a while as well.
Yeah.
One of the things I really want to stress is that building rock cannon takes skill. If you were to chisel the holes in the wrong places or along the wrong fracture lines, like in this next test, well, that could be disastrous.
For a rock cannon, you want something that's going to maintain the hole and keep it there, and you can reuse it. Let's say you've got your sedimentary rock in multiple layers and you bore that way, you're going to end up with fracture and stress lines in the rock where it could easily split apart. So I've cast some concrete that has purposely been cast in layers just to demonstrate that if you make a weak rock cannon, it will not do the job.
Right, all the cameras rolling. How far away should I be?
About 20 to 30 yards back.
Okay, good luck. I saw the rock split and come back together there. It was weak because that's the way it's been cast, but the amount of force that bolted that outwards. Final test then, what can we do with modern science?
Well, I think we can add a few firework effects in, give it a bit of colour. We'll reload the 55-shot Welsh cannon and try again.
Lovely. I can't believe this GoPro's still working. It's still good. So I do apologise to the people of Wales. Not only have a couple of Englishmen copied your historical artefact, we've been bold enough to think we might be able to improve it a bit. We hope you'll forgive us, and if not, we hope you'll at least enjoy the show. Right, are we ready?
Yep, there we go.
Yeah, that'll do.
I think we improved on the Welsh. I'm going to claim that.
Thank you very much. I'll shake your hands.
You're not allowed to.
Yep. When I first heard the idea of a turntable ferry, I assumed it was an early design before anyone figured out how to do ferries properly. A modern cross-river ferry is built with a cabin at the side, so cars can drive on and drive off without having to awkwardly reverse. So I figured a turntable ferry like this one is going to be a prototype solution before anyone figured out how to put the cabin at the side. Instead of having the cars reverse off, you turn the whole car deck around. And yes, that does happen here, but the real reason for the turntable is more clever than that. And there's only one of them left anywhere in the world, here in Western Scotland, over the sea to Skye.
There's been a ferry here since the 1700s, people say. A vehicle ferry, certainly since the 1930s. This particular ferry has been here since the 1980s, and it was operated by a man called Roddy McLeod. Now, when the tolls were removed from the Sky Bridge, he felt probably that, you know, the ferry's time was up really, because you could get across the bridge for nothing, so who would pay to go on the ferry? So the local community banded together and thought, we can't have this. Not having the ferry is a social experiment we don't want to be involved in. So a little group of folk got together and saved the ferry and brought it into community ownership, which it still is today.
There is quite a strong current. The current can be up to 9 knots in the strait, but that's exceptional. Current and wind together can make things interesting. The ferry is very seldom pointing in the direction it's actually going because of the wind and because of the tide. We often have to set the boat going in a different direction to allow us to get to where we want to go.
The water here is tidal and the current is fast. Simple ferry designs are great if you've got steady water that's always at the same height. Your boat arrives, puts down a ramp to the shore, and the cars can drive on and off. But if the water's tidal, well, that ramp could need to go 3 or 4 metres up or down depending on the time of day. So the only way it works is if you build infrastructure on the riverbanks, floating pontoons and large ramps that give the cars enough room to drive up and down. That's far too big and expensive for somewhere like this. So the obvious solution is a slipway, a boat ramp, a long, gentle approach to the water. In a lot of places that does work. Sail up to the water's edge, drop a ramp, and everyone stays dry no matter the water's height. But that means you need a long slipway, and importantly, your boat needs to be lined up straight. Here, in this narrow channel, the current can be so strong that isn't possible. Even if you could line up straight reliably, you can only tie the boat off at the front, so the back's probably going to swing out a bit. So what you want to do is what a passenger ferry does. Pull up alongside the slipway and let people get off sideways. Great for people, not so useful for cars. And that's where the turntable comes in.
The turntable is a remarkable piece of Victorian engineering. It was based on the old railway turntable system. Cars could come onto the boat from any jetty at any state of the tide to then be turned round and be able to drive off. Usually it's 2, but 1 person can turn it. A lot of oil and grease is expended in keeping it as smooth as we can. The way that the boat is designed, it draws virtually no draft at all forward and is only 4.5 feet at the stern, so it can come alongside in very shallow water. That was the part of the design that makes them so versatile. Very rare indeed that we can't work. It would have to be an exceptionally low tide. Before the invention of the roll-on, roll-off ferry, these were the original roll-on, roll-off ferries.
Now there's been a bridge across the Skye north of here since 1995. So these days this is mostly used just by locals and as a tourist attraction in the summer. But if you are in this area, well, I'd recommend taking a diversion and driving across this way, because there's only one place in the world where you can drive off a turntable like this. Thank you very much. A spacesuit has to do 3 things. It has to maintain pressure, so your blood doesn't start boiling in the vacuum of space. It has to provide oxygen, so you can breathe. And it has to protect against the environment, extreme heat, extreme cold, and direct sunlight. This won't do any of those. It's just a replica of that one. That's the actual Sokol spacesuit that Tim Peake, the most recent British astronaut, used in space. The folks here at the National Space Centre wouldn't let me try on a real one, which is fair enough. Versions of that suit have been protecting astronauts since the 1970s, and there are variants still used today. It's not designed for hours-long spacewalks. It's basically an emergency personal lifeboat for if the ship you're travelling on springs a leak. And it provides those 3 things: pressure, oxygen, environmental protection. Now, a couple of months ago, I had a video where an AI tried to suggest stories and titles that I could cover. And one of the things it came up with was the long-forgotten history of the British moon landings. Not strictly true, of course, we never actually got there, but one of the team here got in touch, and it turns out that in the 1940s, 15 years before Kennedy said that America chose to go to the moon, the British Interplanetary Society did have similar plans, including our own spacesuit.
The BIS was set up in 1933 by a man called Phil Cleater, and he had this plan. He wanted to get together with like-minded individuals who were interested in spaceflight and what the possible future of spaceflight might be. Rocket technology was suddenly moving forward in a way that actually spaceflight was something tangible and might well be realistic.
The BIS weren't seriously expecting to launch a mission to the moon on their own, but they did want to say, hey, we think this is possible, and we think Britain should do it. And one of their number, illustrator Ralph Smith, drew up plans for a spacesuit.
So we have an exhibition here at the National Space Centre that focuses on the space race, and people tend to think about America and the Soviet Union, and we wanted to tell something of what Britain was up to at the same time. As we were planning for our exhibition, we were leafing through a research document and looking at the history of the BIS, and immediately this picture jumped out of somebody wearing this incredible looking spacesuit that they'd designed, and immediately we just said, we have to make this.
It looks wonderful, but no one ever built it. Until a few years ago.
So I get a call, and where do you start? You've got 2 drawings, basically. Rather than just say, well, I'll make a replica, a facsimile of it, I thought, let's look at the materials that were available at the time. Cotton and rubber, much like a modern spacesuit, is made out of beta fabric and a rubber pressure layer inside. And the pressures inside it can't expand out any further. It can't balloon out. He would have an oxygen supply in his backpack there, so he's being fed this oxygen supply going through, past his face, down through the suit and recycling back into the backpack again for expulsion in the way just like an Apollo suit did. Here you've got what we call the convolutes, and they're to give a bit of movement at the arm. And right up here you've got cloth of silver. If he's getting cold on the surface of the moon, he can then pull this cape around him, and now any heat that's radiating out from the suit, he can then trap that heat in, and it reflects the heat back into the body again. So these little pins here, they are in fact little standoff mushrooms, so when the cape is hanging over them, there's a gap between the surface of the suit and the surface of the cape, and that gap of vacuum means there's no physical thermal transfer from the suit out into the vacuum of space. You'll have noticed that on the front of his chest he's got this rather strange device here. This is an airlock. Imagine the circumstances, you're on the surface of the moon, you find an interesting rock, you open the airlock, you put the rock into the airlock, you close the airlock, now you withdraw your arms inside the suit through these exceptionally large holes here, and using that long front you can examine that rock that you've just taken off the lunar surface. But you'll also notice there is a shooting stick, and it gives you a walking stick come seat. You get tired on the surface of the moon, you open the seat part of the shooting stick and you sit down. They've kind of thought of everything really. So how do you build something like this and stay to those 1940s techniques? We turned to what would have been available at the time, even to this silver finish here on the helmet. And in fact, the people we went to get this vacuum plating done, they were an original company that would have been doing the original if it had ever happened. And in fact, when we took the helmet into them, they said, oh, well, we finally got to do it then.
There's newsreel footage from the 1940s which says the BIS estimated £500,000 to send someone to the moon. In today's money, that's about 20 million. The Apollo program roughly cost the US government 10,000 times that. It's safe to say that the BIS's plans were optimistic. So how well would the British spacesuit have held up against an actual trip to the moon?
We're pretty sure this would be the Mark 1. If this had ever really walked on the moon, this would have been the Mark 8, the Mark 9. Remember, on the moon you only have to pressurise up if you're breathing pure oxygen to about 4.5 pounds per square inch. This easily would have been capable of taking that pressure, but it just would have been pretty immobile. You simply can't lift your arms up very high because of the nature of this deep shoulder means that the arm just can't rise up.
I think the BIS were very serious about going to the moon. They had nowhere near as much information as NASA would have had in the 1950s and 60s about the realities of spaceflight and particularly the challenges of getting to the moon. But certainly these weren't crazy people just throwing around ideas. There was lots of really talented people. They were just nowhere near as complex in terms of the materials that they had, but they weren't available to them at the time. So who knows, had they have had the time and the money to develop the sort of space age materials that went into some of those later suits, more time to practice and actually do some practical experiments, then who knows, quite possibly.
So this starts when I'm looking up old television shows. I'm about 3 research tangents deep, and I find this incredible line in a newspaper article from 1997. The microwave was invented to meet a need to heat hamsters humanely in 1950s laboratories. And I read that and I thought, that's ridiculous. No, it wasn't. Was it? There's a well-known story about the engineer who invented the microwave. Percy Spencer, just after World War II, was working on one of the new military-grade radars while it was active, and he realised that the peanut bar in his back pocket had melted, which implies that the radar also nearly cooked part of him as well. Unshielded radars are really dangerous, but it was the 1940s. The attitude to safety was a bit more lax. Now, it wasn't a surprise that electromagnetic radiation could heat stuff. That had been known for a while. People had actually been using it for medical therapies for a while. Different wavelengths had different effects. But Percy Spencer was the first person to realise you could cook efficiently with wavelengths that were put out by radar, and then realise that you could sell that, and then realise, well, I could turn that into a usable product. Because a massive radar dish is basically the same technology as this microwave. I'm not going to try and take this thing apart. I'm not qualified, and there is a high voltage capacitor in here which can carry enough charge to kill. Don't mess about with these unless you know what you're doing. But inside here, in the bit you can't access, there's a microwave generator called a magnetron. It moves an electric current past a big magnet with a hole in it, and because physics, that produces electromagnetic radiation. Tune the size of the hole in the magnet, you get different frequencies of radiation. The best analogy I've found is that it's like blowing air over glass bottles and changing the pitch by changing the amount of water inside. So that, but with electricity. Look, I don't have a physics degree. Long story short, a magnetron converts electricity into electromagnetic radiation. You send pulses of that radiation out into the sky and you listen for the echoes, you've got radar, and you've helped win World War II. Or you could put a magnetron inside a safe radiation-proof box called a Faraday cage and tune the wavelengths. It was called the radar range. It was the size of a fridge. It had to be actively cooled. It was incredibly expensive, and it was designed for big commercial kitchens. That was 1947. The first microwave as we know it today, a cheap box that you plug in, that was from the late 1960s once magnetron technology had moved on a bit. At no point in that well-referenced, well-known story does anyone mention heating hamsters in laboratories in the 1950s. So that should be pretty easy to disprove, right? It's going to be an urban legend. There are a lot of urban legends like that. So I started doing some journal searches, and pretty quickly I found papers from the 1950s talking about the reanimation of frozen rats and hamsters. Those papers were written by scientists at the National Institute for Medical Research, a government laboratory in Mill Hill in suburban North London, about half a mile that way. I would have filmed closer to that, but unfortunately it was pulled down a few years ago and the whole area is now a load of new build housing. Anyway, National Institute for Medical Research. In the 1950s, that research included cryobiology, the effects of extreme cold on bodies and tissue. Scientists at that lab froze rats and hamsters beyond the point of death. They used ice and a bath of propylene glycol, which is airplane de-icer, held at below zero, and at that point the animal is dead and will not recover on its own. No heart rate, no breathing, core temperature around 1 degree Celsius, somewhere between 10 and 50% of the animal's body water frozen to ice. And then, by applying hot spatulas to the chest or high-intensity hot beams of light, the researchers would try to warm the animals up and bring them back to life. The success rate wasn't great and the animals were often left with burns, but it did sometimes work. We'll get to why they were doing that later, but by 1955, one of the researchers has the idea to use a magnetron, reasoning that it'd be a lot more safe and humane to reheat the whole animal at once rather than risk burning it. Actually, I say one of the researchers, there's a name on that paper that might be a bit familiar. James Lovelock, one of the last independent scientists, born in 1919, back when scientist could be an entire job description rather than botanist or physicist or computational linguist. Someone who worked across disciplines on whatever they found interesting or whatever they were hired to do. Lovelock is best known for inventing Gaia theory, the idea of Earth as a self-regulating system. He also invented the electron capture detector, which found CFCs in the atmosphere and helped discover the ozone hole. Hardware that he helped design for NASA is sitting on Mars because it landed there with the Viking probes in 1976. And one of the earlier projects in his career, back in the 1950s, was at the National Institute for Medical Research, freezing rats and hamsters. And he had the idea to use microwave to reheat them. But the papers and anecdotes from back then all seem to contradict each other. The timeline is difficult to piece together. There are reliable sources with completely different stories and claims. So I went to ask him about it.
Do you know, you're the first person to come and ask me about the freezing work?
Because James Lovelock, at 101 years old, lives somewhere vaguely around here on the south coast of England, goes for a walk along the coast every day, and was happy to be interviewed.
One biologist, Audrey Smith, was able to revive a hamster that had been frozen. When they woke up, they got a gigantic burn all across their chest, and that must have been pretty painful. And it was messy. I thought, this is a lousy way to do it. So I said, why don't you use diathermy? For 10 shillings of my own money, I bought a surplus RAF transmitter. Joined it up, and sure enough it poured out 30 watts at 30 megahertz, which is just about right. And I took it into the lab the next day and I said, look, here's your diathermy. I thought this is very untidy. Made some inquiries, and sure enough there were 10 centimetre magnetrons that had been invented by Boot and Randall at Birmingham University during the war. To get hold of one of those is not easy. And this is where being in the government department helped a bit. So I just made a few inquiries, how do I get hold of them? And they said, oh, they're working on them down at just above Portsmouth. I said, any chance of borrowing one of your magnetrons? And he said, oh, no. He said, we can give you one if you want. It's an interesting cause, why not? I've joined this up into with a waveguide into a metal box. It wasn't so much a box, it was just a thing made out of chicken wire. Except it's finer than chicken wire, a bit closer mesh. And that was just like the box of a microwave oven. And I fed the microwaves into it, and I told Audrey, now put your hamster in there.
That's a microwave. James Lovelock may not have invented the first microwave, but he certainly invented a microwave. The idea of using magnetrons to heat stuff wasn't his, but no one else was putting one in a Faraday cage box on a desktop. Big commercial microwaves for restaurant kitchens aren't the same thing, and besides, they weren't even on sale in the UK until a few years later.
I put a potato in it and baked it. And it was perfectly all right.
The safety procedures were occasionally a bit lax by modern standards.
In the course of the experiments while we were building it, the thing was running open and the radiation was bouncing all around the room, and the light bulbs would light up without warning. The filament just had the same wavelength as the radiation, and it would absorb it and light up. And pound notes were the funniest one. They'd catch fire, because the metal strip inside was just about the wavelength of the magnetron.
And here's the really amazing thing. It worked.
So we put the hamster in there, frozen solid, and I mean frozen solid, it was like a bit of wood when you dropped it on the bench. Turned the thing up to full power on the microwave, which was about a kilowatt coming out of it. And there was a timer, and after so many seconds, the hamster woke up and started wandering around.
Do I need to say don't try this at home? I mean, there are enough people of all ages watching that statistically, yes, I do need to say it, don't try this at home. It's unnecessary cruelty, you won't be doing medical research, you will be doing a crime. Context is really important. But also, the research has been done more than 50 years ago. There are charts of survival rate and heating, and it turns out that with a microwave, because that's what this was, with a precise calibrated microwave and with artificial respiration to start pumping oxygen around the body, almost every rodent they froze was successfully reanimated. That's the word that the biologists used: reanimation, healthy, behaving as usual, and given a retirement at an animal home, according to one of the papers, back from being frozen to death, sometimes multiple times. So the last question is, why?
Well, this could be of immense importance to also to medicine itself, for preserving tissues for transfer, and also for blood transfusions, because at the moment blood is kept at the blood bank for 3 weeks and then thrown down the sink.
Imagine if that had worked on bigger animals. Back then, humanity did not know what the limits were. This was an open question. The reason that all those 1960s science fiction writers and comic book authors had people being frozen in time or astronauts being sent off in cryosleep, well, it might be because for a little while it looked like that might actually be possible. If freezing and diathermic reheating worked on hamsters, then maybe it'd work on rabbits. If it worked on rabbits, then maybe it'd work on primates. And if it worked on primates, then maybe it'd work on humans. It didn't. Unfortunately, it doesn't scale up.
You cannot freeze a human. It's partly a matter of how quickly you can get the antifreeze agent to diffuse into the cells. Humans too big. It's just a matter of size. A hamster is an acceptable size.
Sometimes research hits a brick wall. Find out a neat thing about hamsters? Check. Casually invent a microwave and then don't commercialise it? Check. Find a way to safely send astronauts to other planets? Not this time, unfortunately, but the researchers tried, and it feels like a story that shouldn't be buried as a vague anecdote in a newspaper from years ago.
I think in an awful lot of science, where there's a success, it's not a scientific thing, it's an invention, which is something quite different. And I think, personally, I'm much more of an inventor than a scientist.
For a Hollywood effect, we don't actually use the Semtex because it does a lot of damage. It's designed to do damage for its military purpose. We don't want that. We want something that looks nice but does the minimum amount of damage possible. So what we're going to use is some detonating cord to burst a bag full of petrol, and that will be ignited as it goes out by an ignition charge off to one side. And we're going to do this in 3 pots called mortar pots, and that will direct the fuel as it flies out, and then it gets ignited, and that produces a nice big explosive effect. So loads of flames and fire and dirty smoke. We do that just pointing towards the camera. We don't want to bother sending it backwards or to the sides particularly. We only want it where it's going to do the effect that we want. For the 3 pots full of fuel, we're probably going to use less than 10 grams in each of them. The reason we're getting a bigger effect using less explosive is because of the fuel. We're putting that in there because that will catch fire, big yellow flames, lots of dirty black smoke, because it's a mixture of kerosene, petrol, diesel and any other muck I happen to have lying around. Those are in plastic bags in front of the explosive charge. The explosive charge is just there to propel the fuel out, vaporise it, make a big cloud of it, which can then be ignited. So the visual effect is from the cloud of fuel igniting, and the explosive is just used to create that cloud. This is detonating cord. It's a thin plastic tube with some fibre winding inside it, but down the very centre it's powdered PETN, pentaethyl tetranitramine, a high explosive, and when this stuff goes off it will detonate along its length at about 6 kilometres a second, so it's pretty powerful. But what we're going to do for the Hollywood effect is to reel it up and make like little flat pads of it. When that detonates, the blast from it will fracture the plastic bag and spread the fuel out and create our cloud of vapour that we want to ignite. The important thing to remember is when you're using things like detonating cord or high explosives in a mortar pot, you need to separate it from the actual steel pot, because the shock waves from the high explosive going off can actually travel into the steel and actually peel bits of it off and create fragmentation. So you need to put a lump of foam between the explosive and the mortar pot to make sure that it doesn't break up and damage the actors you might have close by.
With all the explosives in place, the second trick is how you film it. By moving the camera back and zooming in, you make it look like your actor is much, much closer to the explosion, and it means the whole frame is filled up while everyone's still at a safe distance. Then you shoot in slow motion, you make the explosion seem even longer by shooting from multiple angles and repeating it several times, and you use all the cinematic lens and colour tricks you can to make it look, well, more cinematic. And you tell your actor not to flinch. Across the UK, we take it for granted that if a fire breaks out, you can call an emergency number, firefighters will arrive, they'll do their best to save lives and put out the fire, and you will not get sent a bill for making that call. Sure, if some movie director's arranged a massive pyrotechnic stunt for a movie and they need firefighters standing by just in case something goes wrong, they'll probably pay for the time there. But in everyday life, firefighters are funded by government through taxes for everyone. But that's not always been the case. The Great Fire of London in 1666 lasted for 4 days. The idea of firefighters hadn't really been invented at that point. The Great Fire was only stopped by a change in the wind and by the military blowing up houses to create a firebreak. The whole of central London burned to the ground. Rebuilding took 30 years. The enormous monument on the site where the fire started is still standing today, 350 years later. After the Great Fire, the job of fire protection in London was taken up by insurance companies. Building owners would pay a fee for a few years' coverage, and the insurance company would attach a metal fire mark to the front of the building, like these on the wall of St James's Palace. So in 18th century London, if a fire broke out and smoke started rising, several fire brigades, each run by a different insurance company, would all rush to the scene, and then they'd check for fire marks and only fight the fire if they saw their own company's mark, or the mark of a company they had an agreement with. If the building wasn't insured, they would let it burn. Their job was protection of property, not life. If a neighbouring building was insured with them and the fire looked to be spreading that way, well, yes, they'd make sure that building was safe, of course. And it wasn't just London. There were similar schemes all around the country and around the world. If firefighters standing aside while a building burns seems immoral to you, well, there are lots of places where that's still the case today, or where firefighting companies will send a bill afterwards, assuming that an insurance company will pay it. In places where there aren't enough people, or there's not enough political will for a government-funded fire service, that may still be the only option. In London, it wasn't until 1833 that 10 of those insurance companies joined their fire brigades together to create a single fire service, still private. In 1866, the government finally took over and created the London Fire Engine Establishment as a public service. But that was only after another major fire. It took disaster, it took death and destruction to move things forward to the point where you can call the fire service to save lives, not just property, and without having to worry about the bill. You can still see a few fire marks on old buildings around London and around the UK these days, although not all of them are original. Some are recent reproductions put up for effect. Heck, those on the walls of the palace might be reproductions for all I know, but fortunately it doesn't matter, because firefighters don't have to check for them anymore. There are lots of places in the world which have the same name twice. Places like the Sahara Desert. Well, Sahara comes from the Arabic for desert, so that's the desert. Or the River Avon. Avon originally meant river, so it's the river. There are a few triple names like that in the world, but this, Torpenhow Hill, in the Lake District in the northwest of England, is the only place in the world with 4 words that all mean the same thing. Tor, Old English for hill, Pen, Old Welsh for hill, How, Old English for a slightly different kind of hill, and finally, modern English, hill. Torpenhow Hill. I know it's not a massively impressive place, but the name is good. Except that's a story that's been debunked quite a few times. Double and triple place names are a thing, that's true. They tend to happen because centuries ago locals would name the nearby hill or river or mountain or desert the obvious name, like the hill. And then when folks with other languages arrived for trade or conquest or exploration, they added their word for it as well. But the trouble here is, there is no Torpenhow Hill marked on any official map. The name was almost certainly a modern invention. Someone noticed the village of Torpenhow, about a mile away, and spotted the 3 words for hill there, and then decided to add the modern English hill to it as well. And Tor, Pen and How all have more complicated definitions than hill. It's not really hill, that village. You could plausibly translate Torpenhow as just, well, the land the village sits on, a small rise jutting out of a much bigger incline. This is just a bump on the side of an actual big hill. I don't have a drone with me, but Google Earth shows it well enough. Also, the village's name is Trepenna. It's spelled Torpenhow, but the local pronunciation is Trepenna. So you can tell who's done the research when this is mentioned in a list of weird place names. In reality, there is just the village of Trepenna. Torpenhow Hill doesn't exist. That's the debunk. And so now I'm going to debunk the debunk, because if that's true, why am I out of breath? What did I just climb? I came up here from the village. It's a slow, steady climb on a country road. The land round this point is lower, and it sits right next to Trepenna/Torpenhow. Now, I'm not going to colonise the Lake District and tell them how they should be naming things, but there have been plenty of tourist attractions built around much less than this. A good map is like a good dictionary. It reflects the real world. It doesn't make it. If people will go to that one tree in New Zealand that looks good on Instagram just because they've seen other pictures of it, then probably come to hill. People go to 4 corners in the US just to be in 4 states at once. It's not too weird to think that people would want to visit here. Sure, the village is Trepenna, but this can be Torpenhow Hill if enough people want it to be. And the thing is, as I record this, if you type Torpenhow Hill into online maps, quite a few of them point you here. Actually, just over there, I'll CG in a giant map marker just to make my point. The only thing that's stopping this officially being Torpenhow Hill is that there's not enough consensus. So, who decides that? Because I do worry about coming to places like this. This is a public footpath. I didn't have to ask permission to be here, but I have a duty of care to the locations I visit and to people who live there. That one tree in New Zealand is being slowly destroyed by tourism and by vandals. Trepenna is far enough off the tourist trail, so probably only a few geography nerds will bother to trek out here, but if this did start becoming popular, if tourists did start arriving at Torpenhow Hill, I do wonder how the locals in this quiet little village would feel, because the signpost that says this is a public footpath has mysteriously disappeared since the last time the Google Street View car came by. I'm not saying anyone destroyed it, I'm just saying no one's bothered to replace it. So as for how the locals feel, I probably shouldn't bother them by asking. I grew up in the age of controversial opinion. This should be true for YouTube as well. Not for small channels just starting out, but I do think that if you have the sort of YouTube channel that spends, let's say, a decent amount of money or a decent amount of time on it, it's like $2 a minute maximum, or just a little bit of your time. Oh, look at me, I bought a Lamborghini. Buy some damn subtitles. Also, I could do a whole video on advertising law and product placement. I still intend to at some point. I've been promising it for ages, but I do want to highlight just one specific rule: 12 minutes per hour. The maximum amount of commercials allowed on all British channels. For some of the older channels, it's even less. It's 7 or 8 minutes per hour. And that's it. There are a few other rules about how far apart commercial brakes can be from each other and how long they can be, and occasional small loopholes for odd circumstances, but the big number is 12 minutes per hour maximum. And that's not some rolling average total, that's per hour on the clock, which means that channels will juggle their schedule by a couple of minutes to fit things in. If there's a less popular show right before a primetime ratings grabber, that less popular show might have no adverts in the middle at all. Sure, they might still take a break, show a couple of trailers for their own channel that don't count towards that big time on the clock, but the schedulers will make sure that there's as much advertising as possible just before the top of the hour, just before the big show, and then just after the top of the next hour. There is an art to fitting all that in. And out of all these rules, this is the one thing that you cannot get away with. The regulator checks, they will notice, and many channels have been pulled up on it. But there was one thing that I did notice while I was researching this. There is one other line in those rules which says that commercial breaks must be taken in a way that doesn't disrupt the flow of the programme. It explicitly rules out that Who Wants to Be a Millionaire trick by someone who's just chosen their answer, and it's all dramatic, and the host says, "Time for a break." Like, it's really clear that's not allowed. There's no other way to read that sentence, but the show's hosts have been doing that for 20 years now, and they've never been called on it. There are some rules, apparently, where entertainment can come first. In England, if you want to sell alcohol to the public, you need a licence. You can't just set up a bar or a pub anywhere. And the law about that is set down in the Licensing Act 2003. There are a lot of details in there, including some exceptions. For example, Section 173 makes it clear that as long as you're on a journey, you do not need a licence to sell alcohol aboard a train, a plane, or a hovercraft.
Anybody can go fast, but it's when you come to the first corner, that's when you're going to get ejected. It's like drifting cars. It's all about steering a hovercraft. It's not about going fast, it's learning how to steer them.
The thing is, with hovercraft, if you're looking at it, you're likely to hit it. In a hovercraft, to fly them, you do lean with them, which makes the craft pitch and makes it turn. So if you're serving out the back of one and you lean to give it to someone, it might cause some interesting control of the hovercraft, but it's all part of the fun.
Yeah, you'll be fine in the back of there. We'll just keep it as straight as we can and serve your customers.
And you might think, Tom, you're just doing this for show, aren't you? You're not actually selling alcohol to people. Wrong. This is a real beer pump. There is real beer being fed into it. And this is a working contactless card reader. It is connected to a company bank account. It is absolutely taking payments. Right, let's do this. I did try to do my piece to camera on the hovercraft. You couldn't hear a thing, so I'm going to explain in voiceover how this all works in between the bits where I have to shout at people.
What can I get you?
Full disclosure, there are only trusted friends buying alcohol today, both for safety and because while the selling alcohol part does appear to be legal, I'm pretty sure there are several other trading standards laws that I'm only vaguely following. Don't take this as legal advice. But yes, the contactless card reader really did work, and yes, that is a terrible half-pint of beer. There was a sparkler on the tap and the whole thing had been jostled and vibrated by the hovercraft. Was legal! What
can I get you?
Yeah, that should have been the first clue that I misheard. In £1.50 was not the price for gin and tonic, it was the price of a half pint. Another terrible half pint, that's mostly foam. So as Mark the pilot tried desperately to counterbalance me, I genuinely don't know if he was expecting me to take that glass back somehow, but yeah, we picked that up later. Most of the foam from it got pulled onto me. Oh, and watch the plastic glass between my knees there? Yeah, we picked that up later too. Note that I'm using a thimble measure for the gin there. 3 pour of spirits for drinks like that isn't legal in the UK. You're fine if it's a complicated cocktail, but for something simple like gin and tonic, legally you have to measure it out. And remember, we've got to keep moving at least slightly. The exemption only works if the hovercraft is on a journey, even if that journey is back and forth across a hovercraft racetrack. I did not bring a change of clothes. I drove home smelling faintly of gin and tonic.
What can I get you? Oh, right, that's there.
Yeah, the hover martini was just gin and vodka on ice, and some grass that got kicked up by the hovercraft's fans. I am not a good bartender, and I am amazed how good Mark the pilot was at flying the hovercraft in a strong wind. He's a hovercraft racer, along with Rob, who helped set all this up, and this is a track that is all curves and no straightaways. There was a lot of grass in it. So, the big question, why does this law exist? Why is there this ridiculous exemption?
What can I get you? Vodka and Coke! Vodka and Coke! Vodka and Coke!
Alcohol licenses are granted by local authorities in England, and trains and planes travel through the whole country. It's meant to cover selling alcohol to passengers. And while these days there's only one hovercraft service and it takes 10 minutes, we used to have massive hovercraft that had crossed the channel to France. The law hasn't been updated because it doesn't need to be. After all, who's going to be ridiculous enough to sell alcohol from a moving hovercraft?
The hovercraft is alive!
Monorails are almost always bad ideas. The last time I said that, I got angry emails from monorail enthusiasts, but I stand by it. Yes, passenger monorails are quirky and interesting. They look like something from science fiction. That's why theme parks use them. But they're impractical and expensive because every bit of track has to be either elevated or dug into a trench. And switches at junctions require physically moving the entire track. There are exceptions, of course there are, but for almost every case, a monorail is a worse idea than light rail or trams or even a bus. And that's proven out by the fact that almost everywhere in the world does not use monorails. Except I think I found a good monorail, and it was never public transit. It was a replacement for construction workers with wheelbarrows. The Road Machines monorail was invented in a small town just outside London in the 1940s. It was intended for construction sites. It was in competition with tractors and dump trucks, and yes, workers hauling wheelbarrows, and it's a really clever solution. The track is made of prefab parts, so it could be set up by just clamping bits together, like a giant toy train set. The company claimed that 2 workers could set up 100 yards of track in about half an hour, and because the track is elevated, it could work over mud and rough ground at construction sites where big equipment might get bogged down. The single rail means it can have huge tolerances. It doesn't matter if things weren't set up precisely. If someone needs to set one piece of the track a few degrees off horizontally or vertically, the monorail just clatters through it all. And sure, yes, the diesel engine is quite noisy, but it's designed for construction sites. Oh, and yeah, it's automated. At the end of the track, there's an automatic stop built in where it stops and waits to be sent on its way again. It can even split and merge tracks easily because, well, that's easier when the safety level is designed for bulk goods, not people. By 1966, there were 800 of these monorails in the UK. Some were owned by construction companies that had set them up and taken them down to each job site. Some were installed permanently in factories and works. They've been sold to 60 other countries where they transported timber or clay or sludge, or even at one place in Finland, fish. Basically, they could be used to move any bulk thing that could be loaded into a wagon. There were versions powered by compressed gas and a couple of experimental battery-powered ones, and they showed up in a James Bond film. That futuristic space-age volcano-based monorail was the same type that was being used in construction sites around the world, just with a shiny passenger cabin added on top. But now they are almost forgotten. By the 70s, construction was changing. Tower cranes had appeared, which meant that materials could be moved faster and in 3 dimensions across building sites that were getting taller and taller and taller, and specialised dump trucks were improving too. In 1977, the last of the monorails came off the production line, but they were in use until at least the 1990s. Most were scrapped, but enthusiasts keep a few of them running. This one is at the Amberley Museum in southern England. It's not a regular attraction at this enormous industrial museum, but they have run it specially for me today, which is lovely of them. There are also dozens at a collection in Nantmore in North Wales, including one that's been modified to allow passenger rides. It's one of their enthusiasts who told me about this in the first place. Thank you very much to Derry. It's not that monorails are inherently a bad thing. It's just that in most cases, there are better solutions. Sometimes, like here, they're the right tool for the job. I'm about 30 kilometres outside Reykjavik in Iceland, and yes, earlier today I was swimming in power plant wastewater, which is not something I'd usually recommend. If you were at a coal-fired power plant, well, even if you were just swimming in the water that had been boiled to spin the turbines and then cooled back down again, well, there are enough stories about coal ash contamination with arsenic and mercury and selenium that it would not be safe. For gas and nuclear plants, as long as the water's treated on the way out, you'd probably be fine, I think. It's one of those things where I wouldn't want to chance it. But that blue-white water is in the Blue Lagoon. Now, the management there are very careful about how they phrase it. They prefer to talk about the skincare and health benefits that they claim come from the silica in the water, but yeah, it's geothermal power plant wastewater. Okay, quick diversion here. Most cities in the world have a cold water main supply. There's a grid of cold water to all the houses and buildings that's heated on demand when it's needed in each building. But Iceland is geologically active. In parts of the country, there are high-pressure reservoirs of hot water not too far underground, where underground rivers meet hot rocks. In some places, those reservoirs break through and reach the surface naturally. So near those places, it's economical to drill a borehole down into the ground and capture the superheated high-pressure steam and water that come back up. There are 2 things you can do with that hot water and steam. It's not drinkable, first of all. It's filled with silica and other bits of dissolved rock, but you can put it in a heat exchanger and use it to heat up fresh, clean, cold water, and then you can send the resulting clean, hot water down a pipeline to paying customers. And this is one of those pipelines. There is hot water speeding through this to Reykjavik. It doesn't actually feel warm. If it did, the pipe wouldn't be doing its job because the water only loses a couple of degrees over dozens of kilometres. But yes, hot water speeding through that. Icelandic cities have separate hot water and cold water grids. If your home is connected to that grid, you don't need a water heater. So okay, that's hot water. If you want electricity instead, you can spin a turbine using the high-pressure steam that's coming up and generate clean power that way. And technically, you can do both, but pipelines are expensive, and there is a lot of hot water around here, so often it's just electricity or hot water. Even a massive industrial-sized geothermal borehole will last a few decades before it starts to run out of heat, and when that happens, you can just open another one a few kilometres away. The old one will get back up to temperature sooner or later. The Earth is not going to run out of heat. Which means Iceland has a massive supply of hot water. High up on a hill above Reykjavik, there is this beautiful building called Perlan. It's got exhibitions about the natural wonders of Iceland and a revolving restaurant and observation deck, but the big round things on the outside aren't part of the exhibitions. They're the enormous hot water storage tanks that the building was built around. Perlan is a water tower, just like any other you'd find around the world, except it stores hot water. There's so much of it that while it's not free, it's very, very cheap. If your house is a bit too warm in winter in Iceland, you don't turn the heating down, you just open a window and let some fresh air in. Iceland also has quite a lot of fresh air. When it's snowing, the pavements are heated up by hot water pipes underneath. Last time I was here was in winter. The lake behind City Hall was frozen over and the ice was strong enough to safely walk on. In one corner, there is a pipe constantly pouring a bit of hot water into that lake, just so the ducks have somewhere to swim. And yes, there are natural hot springs elsewhere in Iceland. There are natural hot spring beaches elsewhere in the world, but Reykjavik has an artificial hot water beach. They just pump hot water into that lagoon to heat it up a bit. There's a hot tub down there. But that isn't power plant wastewater. It's regular water like you get